11, 10, 9. We have ignition sequence start. 6, 5, 4, 3, 2, 1, 0. We have commits. We have liftoff. Liftoff at 7 a.m. Eastern Standard Time. 5 seconds into the flight, we're looking good. This is Apollo Saturn Launch Control. We've just passed the 1 hour and 30-minute mark in our countdown for the Apollo 6 mission. We're now at T-minus 1 hour, 29 minutes, 47 seconds, and counting. Our countdown still progressing very satisfactorily at this point, as it has since it was resumed at 11 p.m. Eastern Standard Time last evening. Just a matter of minutes ago, we received a report that we had completed the overall propellant loading of the 363-foot Saturn V launch vehicle. This is an effort that's been in progress for some 6 hours, and during this period, we have loaded a little more than 750,000 gallons of liquid oxygen and liquid hydrogen aboard the 3 stages of the Saturn V vehicle. We started the liquid oxygen loading shortly after resuming the countdown late last evening, loading the LOX aboard from the top down, the 3rd stage, 2nd stage, 1st stage. Then when this operation was completed, we then proceeded to the final phase of the propellant loading, bringing aboard the liquid hydrogen aboard first the S2 2nd stage and then the 3rd stage of the vehicle. We are now completely loaded with propellants and will continue to top off the supply of propellants down to the final moments of the countdown. To recap our situation in the overall countdown, we went into a built-in hold as planned at 5 p.m. Eastern Standard Time yesterday afternoon. At that point, our countdown was at T-minus 8 hours and holding. Several hours prior to going into that hold, we had several key events that did occur. At the T-minus 12-hour mark in the countdown, we started to move back that 9.8 million-pound mobile service structure to its parked position some 7,000 feet from the pad. About an hour after that time, we connected the safe and arm devices for the destruct system aboard the vehicle. This is the pyrotechnic system that will be armed late in the countdown in order to use the destruct system if necessary in flight. Shortly after loading and making our checks with the destruct system, we then began the spacecraft closeout phase. It's about a 2.5-hour operation and includes a crew actually coming aboard the Apollo spacecraft and making final checks of all the switches in the spacecraft itself. This was followed by installation of the quick opening hatch of the Apollo spacecraft. We then pressurized the cabin with nitrogen and performed leak checks. This operation was completed at about 8 hours and 15 minutes in the countdown, and at that point, we were assured that the spacecraft was generally ready for flight. It was the final major checks of the spacecraft occurred at that time. We then had our 6-hour built-in hold and had no problems to deal with during that hold period. Since then, the countdown has been resumed and has been going excellently through the present time. Our weather conditions also look satisfactory for a launch attempt this morning. We expect a temperature in the Kennedy Space Center area of 70 degrees. The winds will be some 15 knots in the pad area with gusts up to 21 knots. This is satisfactory for flight. The weather will be clear. We'll have a visibility of 10 miles in the Kennedy Space Center area. Shortly after completing our propellant loading and coming up over the next 20 minutes or so, will be some final preparations before we pick up our terminal countdown, which begins at 45 minutes in the count. Starting at about the 60-minute mark in the count, we go through a major series of overall checks of radio frequency and tracking instrumentation. These are all the various devices used to track the vehicle in flight and also get information back on the vehicle and spacecraft performance. This is where we stand at the present time with our countdown at T-minus 1 hour, 25 minutes, and counting. This is Launch Control.
Post-manufacturing checkout of the 2nd flight stage is due to be finished early next quarter, following which the stage will be moved to the static stand for firing.
The second flight stage was installed in Marshall's static test stand on May 17th, following completion of post-manufacturing checkout. A single acceptance static firing of 125 seconds duration is scheduled for the stage on June 7th. Pneumostatic testing and cleaning of the second flight stage have been accomplished, following completion of vertical assembly in April. Systems installation, now underway, is expected to be done by July.
A single acceptance static firing of the second flight stage was conducted on June 7th in Marshall's static test stand. After refurbishment, post-firing checkout started August 11th, with completion due in early November. Post-firing checkout of the second flight stage, which was static tested at Marshall last quarter, continued during this report period. Completion of checkout and shipment to the Kennedy Space Center are scheduled in January. Fabrication of structural components and assembly of major structural subassemblies for the second, third, and fourth flight stages continued. Parts, such as these S2 skirts, are manufactured at S&ID's Tulsa, Oklahoma plant. Meanwhile, at S&ID's Seal Beach manufacturing facility, systems installation on the second flight stage was completed, and systems checkout began on July 23rd. Following completion of checkout in late September, the stage will be shipped to MTF in October. Systems checkout of the second flight stage was completed by S&ID at Seal Beach on October 2nd. The stage will be shipped to MTF for acceptance firing when the A2 static test stand becomes available following completion of first flight stage firings. During this time, modification work will be accomplished, which will minimize the amount of work transferred to MTF with the stage.
Due to problems encountered with the first flight stage, the second flight stage was held for modification and rework at the Seal Beach facility of North American Aviation's Space and Information Systems Division. These modifications were completed late this quarter, and the stage was delivered to the Mississippi Test Facility. Here the stage was installed in the A2 static test stand, where the first acceptance test will be performed next quarter. Upon completion of a second acceptance firing, the stage will then be shipped to KSC.
Structural work, including installation of skirt components, continued on the second flight stage early this quarter. Stage joining operations were completed in mid-February, and factory checkout is now underway.
Factory checkout of the second flight stage was completed May 9th at Huntington Beach. The stage is being prepared for shipment to SACTO on May 31st aboard the Super Guppy aircraft for acceptance firing scheduled in late July.
The second flight stage arrived at SACTO on June 1st from DAC's manufacturing facility at Huntington Beach, California. Following installation in beta test stand number 1, the stage underwent pre-firing checkout in preparation for its acceptance firing. On July 29th, a successful acceptance firing was conducted. Following data evaluation, the stage was removed from the stand for post-firing checkout in the vertical checkout lab. Turnover to NASA is expected in late September. Post-firing checkout of the second flight stage, which began last quarter, continued during this report period at Douglas Aircraft Company's Sacramento, California test site. Completion of checkout, modification work, and shipment of the stage to the Kennedy Space Center are scheduled for next quarter.
Structural fabrication of the second Saturn V flight IU, which began March 21st, is nearing completion. Component installation is due to be finished in August.
Structural fabrication and component installation for the second flight IU have been finished by IBM, and checkout is in progress with completion due in October. Work on Saturn V flight IUs continued during the quarter by the contractor, International Business Machines, at its Huntsville, Alabama facility, with checkout of the second flight unit completed November 4th. After modification, the unit will be stored until its scheduled shipment to Kennedy Space Center in January.
Work on the second Saturn V flight instrument unit continued on schedule during the report period by the prime contractor IBM at its Huntsville facility. After installation of modification kits and partial retest, the second flight IU will be delivered to KSC early next quarter.
Located right in front of the press site itself. We request that you don't go up on the mound on the press site, but bring your car into the parking lot in front. We'll start a commentary at about 2 a.m. tomorrow morning, running about every half hour until the crowd grows a little larger, and then we will be giving a complete commentary later in the count. The commentary will be handled from here until we clear the tower at liftoff, at which time it will switch to the Manned Spacecraft Center in Houston. In addition to your own transportation, we will have a bus departing here roughly on the hour, starting at midnight, with its last departure from the news center at 5:30 a.m. tomorrow morning. You all might keep in mind that it's possible that there could be some pretty good traffic in the area as we get close to launch time, and it might behoove you all to consider leaving early enough to not get caught in the traffic at the last minute. We'll have a post-launch briefing at the press site at T+60 minutes. This will be followed by a second conference, a post-mission briefing, which will occur about 10 hours after launch. This will also be a two-way conference with participants from both here at the Cape and the Manned Spacecraft Center in Houston. I'd now like to introduce these gentlemen to you here, and one gentleman who is also standing by for us at the Manned Spacecraft Center in Houston. This will also be a two-way conference where we'll first take questions from here and then switch to your colleagues in Houston so that they'll also have an opportunity to ask questions. To my right here at the Cape is Mr. George M. Lowe, who is Apollo Program Manager for the NASA Manned Spacecraft Center. Next, Mr. William Snyder, Office of Manned Spaceflight, NASA Headquarters. Mr. Snyder is Apollo Mission Director. Next, Rocco Petrone, who is Director of Launch Operations for the Kennedy Space Center and Launch Director for the Apollo 6 flight. Next, we have Dr. Arthur Rudolph. Dr. Rudolph is the Saturn V Program Manager from the Marshall Space Flight Center. And Colonel Royce Olson, who is Director of Department of Defense Manned Spaceflight Support Office at Patrick Air Force Base. Also standing by in Houston is Mr. Cliff Charlesworth, who is the 502 Flight Director, the Apollo 6 Flight Director for this mission at MSC. I'd now like to turn it over to Mr. Snyder. Excuse me, I also understand, I'm sorry, Chris. No, we also have Mr. Chris Kraft, who is Director of Flight Operations for the Manned Spacecraft Center, also standing by and in Houston. Bill, would you take over, please?
Good afternoon, ladies and gentlemen. First, I'd like to apologize for the hour and a half delay. I assure you we were working and weren't just loafing. We have just completed our final review of the spacecraft and the launch vehicle and the entire complex, as well as the network and the DoD forces. And we've completed our review of the weather, and everything is at this time go. The weather situation is, as reported to us by the ESA people, is basically early in the morning, the weather to be much like this, but as it is out here today, that is with clear and gentle winds, with deteriorating conditions toward the afternoon, with an expected wind velocity reaching as much as a peak of 25 knots sometime later in the day. But we are on schedule and moving out for an 0700 launch tomorrow morning. That's 0700 Eastern Standard. The close of the window for tomorrow will be dependent upon the conditions in the recovery zone. We have set a requirement that the conditions in the recovery zone be such that the on-site commander can give us reasonable assurance that he will be able to successfully recover the spacecraft. We expect the close of that window to be, if conditions are very good out there, to be on the order of noon, 12:30. This is, of course, the final qualification flight on the Saturn V launch vehicle, since we have previously qualified the command and service module and the lunar module for manned flight in previous missions. We are looking forward to having a good launch vehicle flight, as a matter of fact, a good spacecraft flight too, George. But as I said, the spacecraft objectives are on this mission secondary. It is even conceivable that, and I stress the word conceivable, that the mission may have accomplished all of its primary mission objectives at the time of insertion into orbit, although, of course, that couldn't be determined for quite a long time. We do have one, I shall not call it a dark cloud, but one question mark, and this was the question that kept us out at the Launch Control Center for the past couple hours, and that was a question of a temperature that we experienced during the countdown demonstration test on the S2 stage J2 engines, where some of the propellant pump discharge temperatures were a few degrees above what we call our red line value, that is the values that we expect to achieve for launch. We have taken some corrective action, and we have examined it. We think we've solved the problem. We have reasonable hope that we've solved the problem. However, there is no way to test whether or not we will achieve the proper red line without going through a cryogenic test. And so the cryogenic test is going to be in the morning. If, for example, we do not achieve this temperature, proper temperature on the first cycle, we will be forced to do what we did during the CDDT, and that is namely cut off, stop at about 22 seconds or thereabouts, and recycle back to about 24 minutes. Then wait, assess the problem, see whether or not we can stabilize conditions again, and try again. Hopefully that will not happen, but it is a very distinct possibility. With that, I'd like to turn it over to Rocco and ask Colonel Petrone if he'd now give us a discussion of how things have been going out at the Cape.
Well, we've been busy, as you know. We had our countdown demonstration Sunday, and then we had to recycle for the count and also work our way through some of the things we saw in the countdown demonstration, but we succeeded in picking up the count at 1 o'clock this morning. We have a final 24-hour terminal count, so we picked up at 1, and as of the time we left there, and as of now I understand, the count is on schedule. Now we plan a hold at the 8-hour mark, T-minus 8 hours.
No, that's not it.
We plan a hold of 6 hours. We have no scheduled work, and at this time it doesn't look like there'll be anything in that hold necessary. We were on schedule, all our checks, everything was going fine. So roughly at 1700, another hour and 15 minutes, we will would complete our task. That's our schedule. We'll have a 6-hour hold, pick up again at 11 o'clock tonight for the final portion of the count of 8 hours, giving us a 7 o'clock liftoff. At 10:30, we plan to take a look at the weather, see if things have changed. Right now, the present forecast would indicate our morning time is the best time to go. That is Thursday morning. But we'll take a look at the weather at 10:30 and commit at 11. I'm speaking Eastern Standard Time, which is T-minus 8 on our count for the launch. At T-minus 7 hours, essentially we start our cryogenic tanking. Shortly thereafter, we'll start getting cryogenics into the stage. Up until T-minus 8 hours, we can sit there and cycle on a 24-hour basis. If for some reason we decide not to pick up the count at 11, and assume we have no problem causing us to go in and change something, we could sit there and hold. We can do that through a Saturday, as we now see it. We could, in other words, Thursday, Friday, Saturday, our launch attempts, assuming for some reason that at T-minus 8 hours we do not want to pick up the count, other than hardware difficulty somewhere in the program. Once we get our cryogenics aboard the stage, we then are in a position of a 72-hour recycle. Just with those comments, that'll tell you where we've been, what we've been doing since our CDT ended, and now we plan to pick up the count for the launch tomorrow morning at 7.
Thanks, Rod. Colonel Olson?
The Department of Defense support for this mission is essentially the same as it was for Apollo 4 501. We have roughly 45 aircraft and 11 ships involved. We are taking advantage of this unmanned mission, of course, to further train our crews and check out the equipment on the new resources that are coming into the inventory to support Apollo, such as the Apollo ships and the Orion aircraft. There will be 2 aircraft in Hawaiian area for reentry. There will be 3 of them out here in the Atlantic. There were 3 Apollo ships involved, one of them, Mercury, sitting right out here in the port that will be just getting some training as the spacecraft passes over in a passive mode. So if you're interested in Apollo ships, there's one right out here in the Cape. That's all I have.
This is Apollo Saturn Launch Control. We're at T-minus 1 hour, 8 minutes and counting. Our countdown still going very well at this time. In progress and just about to be completed is one of the key tests between the Manned Spacecraft Center in Houston, that is the Mission Control Center at Houston, and the crew here at the Launch Control Center at the Kennedy Space Center. It's one of the pre-flight command tests to assure that Mission Control Houston will be able to send and receive data from the launch vehicle itself. That is from the computer, the airborne computer aboard the Saturn V launch vehicle located in the instrument unit. The purpose of this test, it's a computer program test, is to check the ability to receive and acknowledge ground control commands aboard the launch vehicle digital computer. Test appears to be going well. We also have a report on the status of our overall propellants in the vehicle now that we have completed the propellant loading, and all propellants aboard are stable at this time. Of course, as far as the liquid oxygen and liquid hydrogen is concerned aboard the 3 stages of the Saturn V, we will continue to replenish the supplies of both of these over the final phases of the count until we begin to pressurize the tanks just about 2 minutes before the planned liftoff. We're aiming toward a planned liftoff of 7 a.m. Eastern Standard Time this morning. Our countdown still going well at this time. T-minus 1 hour, 6 minutes and counting. This is Launch Control.
Thank you. I believe with that we're ready to proceed to questions. We'll start here at the Cape. Dan, back up here. Would you identify yourself and your organization, please?
Yeah, I'm Dan, partner of the Denver Post. I'd like a recap on the postponements and the seriousness of them and so forth. As I understand it, March 21st and now here about 5 postponements. Is that correct?
I don't know the numbers. It did start out at March 21st, and we did have a number of minor problems. Well, I'll say, normal problems, and perhaps Rocco would like to go into them.
Bill, I just have to, I guess those of us working in the program, doing the job day by day, might don't see the calendar shift. It shifts for us as we go through our schedule. I can't think of anything large like our CDDT. We did have 3 attempts. On one attempt, we had a leak in the facility, and on a coupling we wanted to repair. On the second attempt, we had a switch difficulty. So there's those kind of problems that went on and moved it from the 21st to the 4th throughout our preparation schedule. I can't recall a single large item that we changed out. It was additive work. Things took a little longer, and some of our tests, either we didn't hit it the first time, had to go back in and change a component. But I could point to nothing significantly large that gave us, say, a 2-week slip by itself. There were many additive situations.
Bill?
Bill Hines, Chicago Daily News. I'd like to ask George Lowe that although this is regarded as the objectives are regarded as secondary as far as the spacecraft is concerned, is there anything that could happen to the spacecraft, including loss of it, failure to recover it, that might make you want to have another preparatory flight before manned flight?
Bill, I'd have to say yes to that question, but I can't give you a more specific answer. If we should lose a spacecraft because of a spacecraft failure, we certainly have to look at that failure to determine whether we need another flight or can solve it by ground test or analysis or what have you. So these questions are extremely hard to answer before a flight. They become very easy after a flight.
Back up, right in this same row with Mr. Hines, the gentleman in the blue shirt.
Ben Cade, Time Magazine. Either for Mr. Schneider or Mr. Petrone, can you explain a little further detail the J2 pump discharge problem?
We have a red line that we have to achieve in order to assure that when your turbo pump starts pumping your liquid oxygen or your liquid hydrogen into your engine, that you do not cavitate. The term means that you don't convert the fluids into gases. In other words, you want to deliver liquid. We call it, you want to deliver a good solid liquid. This has to do with temperature and pressure. So we have a temperature reading that we look for at the engine inlet. The red line we were looking for and were set at was minus 286 degrees Fahrenheit. It is now, with looking at the engine specifically and having run through our countdown demonstration Thursday, we have in effect raised that 2 degrees to minus 284. And what you're doing here is looking for a number that will assure the pump functions properly so that the liquid doesn't gasify as it goes through the pump. These are very cold liquids, and as you sit there, you tend to pick up heat just by virtue of the fact that they are cryogenic. So the whole question of a red line on an engine, and it has to do with each particular engine and the head that you have on it, the prime purpose of it is to prevent cavitation or to prevent the liquid from being converted to a gas before you get to the injector of that engine.
Can I follow up on
Yep.
This was on the oxygen side rather than the hydrogen.
We had actually, Bill, 3 on the oxygen side and one on the hydrogen side. We had 1 hydrogen feed line and 3 oxygen feed lines in the second stage, wherein we were, say, a few degrees hotter than the red line limit.
Well, you don't redline hydrogen at any temperature as high as minus 286.
No, the number I gave was oxygen. Hydrogen was minus 420. My memory says minus 420. Can you account for the heat source and follow up on this?
Well,
Really, this is not so easy to explain. We know there must be a change in the heat source. But what it really is, we are still struggling with. It could be...
Is this a novel situation? Has it ever happened before?
It has not happened before.
Well, it didn't happen. Let's say
No, no, no,
it
no,
didn't happen on,
501.
it did not happen on 501. However, it has been seen on prior programs.
This is Apollo Saturn Launch Control at T-minus 60 minutes and counting. T-minus 60 minutes and counting, and the countdown is still progressing satisfactorily at this time. We are about 15 minutes away from the terminal countdown for the Apollo 6 mission. At this point in the countdown, we are about to start a series of major range radio frequency and tracking checks of the overall vehicle and the spacecraft. These checks will continue through a major portion of the final countdown. This is to assure that all our tracking instrumentation and all the instrumentation aboard the Saturn V that will relay back information in flight are all operating satisfactorily. In about 5 minutes from this time, the primary damper arm. This is an arm located at the top of the mobile launcher above the Saturn V vehicle, and it has been attached to the vehicle through the count phase up to this time. The primary damper arm will be removed. It will be lifted away from the vehicle. It has been used up to this time to support the vehicle, and it is no longer required at this phase in the countdown. So we will be pulling back that damper arm shortly. A check as far as our propellants aboard the vehicle are concerned. All propellants are stable at this time, and the count is continuing. We're now at T-minus 58 minutes, 35 seconds and counting. This is launch control.
Maybe I can say the following. Since this compartment where these engines are, we can test only here at the Cape for the first time, not in our captive firings, on our test stands, and therefore the conditions are entirely different because now the engines are enclosed and are between an oxygen tank on the second stage and an oxygen tank on the first stage. So we have to deliver heat to protect against too much cold. Now any slight change in the construction, see an insulation change, would affect the condition in there. Now we have taken corrective action by improving insulation, and as Rocco already mentioned, we changed the red line so we can accept a higher temperature. But what it will really turn out tomorrow morning, we don't know for sure.
Sanders, go ahead. Do you have a question?
One part may have been answered. You changed the red line. Was that the figure you gave Rocco, 2 degrees difference? And how much different was it? Was it the CDDT when this turned up? How many degrees was it past the red line base?
I think we were about 4 or 5 degrees below, or hotter than. You have to be careful. You're working in negative. We were 5 degrees warmer than we wanted to be, and there was some variation between the engine, but about 5 degrees.
That was the worst one. The others were better. Now here we have done some improved insulating, and I think this will contribute to a better condition. And also again we changed the red line. We give 2 degrees, so that we think will get us in the start box, what we call it. The engines are very sensitive to temperatures and pressures, and that should do the trick. Again, we are not sure.
Is this only on the S2?
That's only on the S2.
Al, right over here, Ben.
Albert Salestead, Baltimore Sun. What is getting too hot, the cryogenics or some of the metals?
The cryogenics. The cryogenics under the head and under the pressures, in effect, get superheated. That's what there's increase in temperature.
Howard.
Howard Benedict, AP. This is for Mr. Snyder. Last week, Bob Mosier told us that his people are anxious to get the 503 vehicle out on the pad within 10 days if it has to be unmanned, and they'd like to have a decision from you within 7 days whether it's going to be manned or unmanned. Think you can give them one in that time?
Well, I'll hasten to state that the decision is not mine. All I can say is that the decision will be made as soon as there is an adequate analysis of the data so that we can determine whether or not the mission satisfied all of our requirements. As a little aside, it's difficult sometimes at the completion of a mission to determine whether or not it is a completely successful mission, because you've got to await analysis of all of the data. You can have what appears to be a perfect mission, and if you had a telemetry link go out or a multiplexer go out and have no data, from a technical standpoint, it's a complete failure. Similarly, on the other hand, you can have one where things change considerably during the mission, such as what happened on Apollo 5, but yet get all of the data that you've been really looking for in the flight. So it will take some time to make that decision, and we all know how everybody wants the decision as early as possible. So that's all I can say now.
Mary? Did you have a follow-up? I'm sorry. Go ahead.
Follow that up. If you don't say have the decision within 10 or 12 days, but it still looks good, would you hold up the rollout of the 503 to the pad?
I think we'd hold that decision and make that when we see how good the data is or how bad the data is. We'll make that depending upon how it looks.
Go ahead, Mary.
Mary Bob, Fairchild Publications. Regarding the engine again, did this affect all engines? And secondly, at what point will you know whether it has been solved?
It affected 3 of the 5 on the liquid oxygen feed docks, and 1 of the 5 on liquid hydrogen. And we will not know that we have solved it sufficiently to proceed with the mission until 22 seconds before liftoff.
Jules?
Jules Bergman, ABC News. For Bill Schneider. Bill, you said it's possible all the primary mission objectives will be accomplished by insertion into orbit. What has to be accomplished by insertion into orbit to meet all your primary objectives?
Well, let me hasten to add that all of the primary objectives as listed in your press kit do include an S4B restart, and we will be mightily disappointed and will not consider the mission a complete success if we do not get that. What I am saying is that if for some reason or other we do not get a restart, we may, and I hasten to say we may have sufficient information to make a proper decision on whether or not the Saturn V is ready for manned rating. We will not know that until long after the flight, because that would be as a result of careful analysis of the data.
Go ahead, Dick.
I'd like to go back to the heating problem just for a moment. When this problem occurs, as I understand it, when the cryogenics are being pumped into the tanks. Well, the problem actually is seen. We go into automatic sequence at 3 minutes and I believe 7 seconds. We start a pressurization activity. The cryogenics heat up under the pressures. These are the flight pressures that we're building up. Now what we have to do is read, and we do this on every flight, we read the temperature at the inlet to the engine. We establish a bandwidth, we call it the red line, and we say we must be within that bandwidth or below that red line in order to function properly. Now on the S2, you're reading a value on the ground, but actually the engine isn't going to ignite for some 2.5 minutes, so what you're doing is extrapolating a ground condition into what it would be 2.5 minutes later. But you'll see your temperature rise in your automatic sequence. It's the only time we can see it. That's the reason Dr. Rudolph mentioned we've got to go through our terminal sequence, and we'll be reading these values, and our times are down to minus 22 seconds. If we then are within the red line, we would proceed. If we are not, we plan to cut off.
Apollo Saturn launch control. We're at T-minus 50 minutes and counting. T-minus 50 minutes and counting, and the countdown for the Apollo 6 mission is continuing at this time. Just a matter of several minutes ago, we did receive word, and we're able to watch it on closed-circuit television here in the Launch Control Center, as the primary damper arm that secures the vehicle to its launch tower was retracted. This came at the planned time, and the vehicle is now essentially standing free except for its 4 hold-down arms, which of course hold it to its launch base, and some 6 service arms that still are connected and will remain connected through the final phases of the countdown. Coming up in a matter of minutes will be the start of our terminal countdown, which is called for in the procedures at the 45-minute mark in the count. At the start of the terminal countdown, we will first make a complete check of overall spacecraft systems to ensure that all the tracking systems concerned with the spacecraft are operating satisfactorily. Our countdown is still going well at this time, as it has since the count was picked up at 11 p.m. last evening. We completed our propellant loading on time with no problems. The major portion of the last 6 hours of the countdown have been concerned with bringing the propellants, that is the liquid oxygen and liquid hydrogen, aboard the 3 stages of the Saturn V vehicle. The propellant loading went very well, and we are continuing to monitor all propellant systems at this time and are receiving reports that the propellant system is stable. We're at T-minus 48 minutes, 20 seconds, and counting. This is launch control.
What does the fuel at the time the fuel is injected into the engine? In which state is it? Is it liquid, or is it liquid and then it gasifies in the engine?
You go through the injector as a liquid with your liquid oxygen. The difficulty comes at your pump. If you start to cavitate or build up an air bubble there, the pump will not work efficiently. And therefore your mixing ratios are entirely different than what you planned. And you can get any mixing ratio, which could lead, of course, to many consequences, whether it would go in the engine properly, or whether you would get too much fuel, not enough oxygen. But basically what you're doing is you're upsetting your ratio of fuel to oxidizer going into the engine.
And you want to start fuel-rich, not oxygen-rich, George. Both are liquid.
George Alexander, back up there, Ben, please. And would you please wait for the mic? I think your colleagues in Houston are missing a few of the start of the questions.
George Alexander, Newsweek, for George Lowe. George, what's the status of the spacecraft for the 503 mission? Where is it? How soon can you bring it out to the VAV to stack it, assuming that the flight tomorrow is a success?
You're talking about spacecraft for an unmanned or manned flight? Well, George, that would be Command Module 103, which is about to go into checkout in Downey, and LEM 3, which has been in checkout in Bethpage for some time. Neither one of these vehicles are scheduled for delivery here until summertime.
Bill?
Bill Hines, Chicago Daily News. I'm a little confused then on the basis of Howie Benedict's question and then the answer to this last one. What is the sweat about moving the next Saturn V out to the pad if you don't have the command modules and the lunar module for the manned flight here?
Well, because of some of the interactions in getting some of our work done out at our remote sites, on some of the programs that must be put in, we have a situation where our missions are pressing one on another.
I believe I believe, Bill, the way with that, we have got a boilerplate on 503 now.
Yes.
And if the decision were made to fly it unmanned, and what we have planned and brought to this point, we have on board a boilerplate spacecraft with all the weights and the simulations in there, and that's what would fly.
Then you'd want to get that out in a hurry and get it off in order to make way for 504, which would then be your first manned flight. But
that is our planning as of today. We brought 503 to the point of checkout, where it's near rollout within these 10 days that Howard mentioned.
This is Apollo Saturn Launch Control. We are go for the terminal countdown for the Apollo 6 flight. We just passed the 45-minute mark in the countdown. Now T-minus 44 minutes, 50 seconds, and counting. In progress at this time are some final checks of the overall tracking systems of the Apollo spacecraft. Coming up in a matter of minutes following the successful completion of these tests will be some final checks of the destruct systems aboard the 3 stages of the Saturn V vehicle. These are checks between the range and the crew here in the Launch Control Center with the launch vehicle itself to assure that the destruct system will be capable of operating if required in flight. This is a test that lasts some 5 to 7 minutes of final verification of the destruct system. The destruct system, of course, is not armed at this time. It is armed very late in the countdown, but final checks are made at this point. Now at T-minus 44 minutes and counting, this is Launch Control.
Now we'll look at the results of 502 before we make further decisions. We have brought it to the point with a boilerplate that would fly for the in the eventuality we have to launch it. It would not wait on another delivery of a spacecraft. I believe that was the question you were raising.
Well, let me just... But in other words, if you decided that you were going to have another, if you decided that your next flight was going to be the manned one, then you would not be in a hurry to get the Saturn V out of the valve.
That's correct.
Okay.
Steve?
Two more brief questions. Steve Rowan, CBS. 2 more brief questions on the temperature problem. Rocco, I'm still not sure whether one of the J2 engines or 2 of them were not affected in any way by this problem. And secondly, do you have any indication of why they were not affected and the others were?
It turns out that the 3 that were affected by liquid oxygen and 2 were not. The one that was affected by liquid hydrogen was not affected by liquid oxygen. So we had the center engine was the one that we ran hotter on the liquid hydrogen. That did not have, was within the red line for liquid oxygen. So what you have is a case of 3 engines where they're out of spec on liquid oxygen and 1 engine out of spec on liquid hydrogen, not the same engine.
Can you explain in any way why the 5th engine did not have this problem on either side?
No,
the 5th engine had a problem on the hydrogen side.
The other
center engine on the hydrogen side. And it has a longer feed duct. The feed ducts come down the side of the stage and then go to the engines. And they come not all down on one side, but are distributed. Now then the lines are equally long for the 4 outer engines. But the center engine, being farther away, needs a longer feed duct. So it is therefore more sensitive to any temperature changes which might occur in that stretch of the line to the center engine.
It's a function of geometry and heat distribution. As Dr. Rudolph mentioned, the flow in that interstage, the only time you see it is here at the launch site. The only time you have a first stage to sit on top of. Therefore, the chill conditions you get, we have electronics in there and actuators we must keep warm, so we must pump warm air in there. Now you get a series of factors which end up with a result. There's going to be some movement of those values, the inlet temperatures. And literally one can only experiment with it here to see what the end result's going to be. It cannot be done on the test site.
We had 2 patient hands in the front row, and there's a 3rd hand up now. We'll take these 2 questions here, then we'll go to Houston for questions, then we'll come back here for anybody who has questions. Go ahead, Ed.
Another question on this heat problem. If you go to T-minus 22 seconds and have to hold, will that be a prolonged hold? Or?
We will not hold at T-minus 22.
I'll try to.
At T-minus 22 seconds, anywhere after the 3 minutes 7 seconds, we will revert back and we'll go back to T-minus 24 minutes.
Well, is there some quick fix, or you have something in mind that you can make a change to get the temperature down again?
By observing the particular trace of the temperature, we'll be watching the temperature on a recorder and have it plotted. There are adjustments such as inlet temperature into that inner stage. That's one adjustment we can make, yes.
Go ahead, Sue.
Excuse me.
Go ahead.
We also expect, as we had during the CDDD, that on the second run, let me call it, the situation has improved. It did on the first attempt, or on the second attempt rather, during the CDDD, improve the only one LOX site was out of the spec for the red line.
This is Sue Butler, the Daytona Beach News Journal and McGraw-Hill. I believe this is for Dr. Rudolph. At an earlier briefing, Bob Mosier told us that if we go manned on 503, the S2 stage will go back to Michoud for certain man rating and certain modifications. He specifically mentioned possible relocation or strengthening of the baffles, the LOX baffles, which had given some trouble on 501. Could you pinpoint this and explain a little bit about it?
Yes, we'll talk two different issues at the same time. So let me talk first about the one where you mentioned the second stage, the S2 would go back to the test site. That's correct. We would, in the case that the 503 would be manned, take the second stage, ship it back to the Mississippi test facility and make a cryogenic proof test. So that answers one question, I believe. The other one is that during the 501 LOX loading in the S2, we had damage of baffles. And in order to save time during the countdown and avoid crew fatigue, we want to go to a fast fill on 503 manned. Now, since we had this problem with the baffle damage on 501, we have to do something to the baffles. Strengthening, for instance.
What?
It is.
How?
Well, we for instance, changed the baffles, which are shaped like a rhomboid, and sit down at the bottom of the LOX sump. We took the lower half off. So in a way, we took them out of the stream of the incoming liquid oxygen. Well, that helps. But we also have to study the flow dynamics inside. It isn't all that simple as I say it here. And again, here you can only find it out by testing, not by analysis, by sitting down on your desk and trying to, in your mind, to figure out what the forces are. Anyway, we think we have, by also making certain changes to the facility, Rocco, understand the problem well enough that on 503 manned, we can fast load again.
This is Apollo Saturn launch control at T-minus 35 minutes and counting. T-minus 35 and counting. All aspects of the Apollo 6 mission look good at this time. The propellants are normal and the replenishing sequence is continuing. Just a matter of minutes ago, we received a report that the spacecraft checks and final checks of the range safety command destruct system aboard the vehicle have been completed. In progress at this time is one of the major steps in the countdown, an all-important power transfer in which the crew here in the Launch Control Center switches from external power to the flight batteries aboard the vehicle to assure that they will all operate satisfactorily. And of course, they are vital during the powered phase of the flight. At this point, we go internal with the vehicle to assure that all these batteries operate properly. We remain on internal power for about 30 seconds and then come back to external power in order to conserve those batteries for the actual flight. The final transfer to internal power will occur at about the 50-second mark in the countdown. Just a short while ago also, astronauts Jim McDivitt, Dave Scott, and Rusty Swikert, the prime crew for the first Apollo Saturn V manned flight, came into the control center. They'll view the launch from the control center here at the Kennedy Space Center. They were accompanied by Deke Slayton, who is Director of Flight Crew Operations for the Manned Spacecraft Center. Our countdown still proceeding, aiming toward a planned liftoff at 7 a.m. Eastern Standard Time. We're now at T-minus 33 minutes, 18 seconds and counting. This is launch control. This is Apollo Saturn launch control. We're approaching the 30-minute mark in our countdown. It'll be 30 minutes and counting, about 30 seconds from this time. If you care to synchronize your watches at 30 minutes past the hour, we'll count down the last 5 seconds or so for you. At this point, our countdown is still continuing, and we'll come back on to countdown for the 30 minutes past the hour mark. This is launch control, coming up on 10 seconds away from 30 minutes past the hour. 5, 4, 3, 2, 1 mark. 30 minutes past the hour, T-minus 30 minutes and counting. We have completed our power transfer test. It went very satisfactory, and the count is continuing at this time. This is launch control.
Thank you. We'll now switch to Houston. I understand both Mr. Kraft and Mr. Charlesworth have a statement.
This is Houston. We have one logistical announcement here first. The Houston News Center will be open until 10 p.m. Central Time this evening and reopen at 4 a.m. Central Time tomorrow morning. Next we'll hear from Mr. Kraft and then Mr. Charlesworth.
I'd like to point out that this is another unmanned flight of a manned vehicle, and therefore another complex job for the flight control and ground crew to accomplish. There are a large number of things that we can and may have to do, and it may be a difficult mission from that point of view. The other point I'd like to make is that we have been making a large number of modifications to the world network over the last 2 years, and this flight in itself is sort of a dress rehearsal for our upcoming first manned flight of the 101 spacecraft. We've made a lot of changes, we've added a lot of equipment, and we feel now that this flight will be proof that all of that equipment is ready to support our manned spaceflight program.
About all I would like to add is that we've completed our training to date with what I think is good results. I think the team is prepared to do whatever is required to be done. In terms of the facilities, our ground support facilities, computers, network, and so forth, we're proceeding along normally with our part of the count to meet the pad. We have no problems at this time, and based on past testing and support in CDDT, we don't really expect any, and we expect to be ready to meet the pad and launch in the morning and have a good flight.
Okay, we're open now here in Houston for questions.
Kansas City Star. Mr. Kraft, assuming a launch tomorrow morning, has anyone recalculated the apogee and perigee of the S4B and how many degrees it'll miss the moon and whether it'll come back to Earth?
Mr. Charlesworth has.
I've got a few numbers. I was sure someone would ask. Assuming we launch on time, the best information I have is to expect the apogee of the 4B to be some 279,000 nautical miles, with a perigee that is back, when it comes back to the Earth, of around 1,700 miles, with a period of some 16 days. Now, we don't expect it to enter essentially the moon's sphere of influence if we go on time. Now, if you try to pin me down for launch delays or different days, I can't honestly answer it because it's a variable depending on the time of the day you launch, location of the moon, day of the month, and so forth.
Cliff, what about Arthur Hill from the Houston Chronicle? What about in re-entering the atmosphere? Will it come back and do that under the present plans?
The first time out, it doesn't look like it will, but the next time around, if we get into the sphere of the moon's influence, it perturbs the trajectory. It could. It's probably a good probability that it'll come in.
Any further questions from Houston here? Houston turns it back to the Cape at this time.
This is Apollo Saturn Launch Control at T-minus 25 minutes and counting. T-minus 25. All aspects of the mission are ready for flight at this time. This includes the Mission Control Center in Houston, the Worldwide Tracking Net, as well as the Air Force Eastern Test Range support elements, both here at the Cape and downrange, and the 450-man crew here in the Kennedy Space Center's Launch Control Center for the final phase of the countdown for the Apollo 6. At this point in the countdown, we have just received confirmation that final checks of the C-band radars that will track the vehicle in flight have been completed. These are the radars at the Cape that will follow the Saturn V and actually check with the instrument unit and the Apollo spacecraft during the powered phase of the Apollo 6 mission. We're now at T-minus 24 minutes, 6 seconds, and counting. This is launch control.
We'll check. Go ahead, Jules.
For Bill Schneider, Jules Bergman again. Bill, just so I clearly understand this point, if you don't get a second stage burn of the S4B, have you met your primary mission objectives? Can you man rate for Saturn V and start manned flights with 503?
The answer to the first one is no, we have not. We would not have met the primary mission objectives as stated in the document, in our own documents, because they do include an S4B restart. The answer to the second question is it is perfectly conceivable that after analysis of the data, we could find that the reason for restart had no implications on whether or not the vehicle was man-rateable. The first planned Saturn V mission does not currently include a manned restart of the S4B.
Go ahead, Jules.
The second part's for George Lowe. Why is the new hatch being flown aboard this spacecraft, other than the fact that it was ready? It's being tested in any way.
I guess you've almost answered your own question, Jules. We did, at the time that we made the decision on the new hatch, know that we could not get it on spacecraft 17. We knew we could get it on spacecraft 20, so we moved out and put it on 20 to get the best possible test of the hatch at these speeds, heat transfer rates, and so on. But we've completed some very satisfactory ground tests. We've got more to go, and also we've seen the very low heating rates in that area on spacecraft 17, so that since that decision was made, we have convinced ourselves that we don't need a flight test of this hatch for man rating purposes.
Go ahead, Dick.
Dick Lewis, Chicago Sun-Times. I have two short questions. One is, the first one is, what is the now official lifting capacity of the Saturn V? Started out to be in lunar to the moon. Pardon?
100,000 pounds.
100,000 pounds, and this is an increase of...
It's lunar trajectory.
It's an increase of 10,000 pounds since, about the last 3 or 4 years, is it?
No, it was for the last 2 years, if my memory serves me right, 98,000 pounds.
Second question, this S4B trajectory, and I suppose perhaps this might go to Mr. Charlesworth in Houston. This, I believe, is one of the few, or possibly the only, circumlunar trajectory that we've flown. Possibly there have been one or maybe a scientific experiment has flown this way. But this is, as I understand it, this is an orbit which goes around both the Earth and the Moon. Is it not? Am I wrong about that? I see Mr. Schneider shaking his head.
Let Cliff answer.
The rest of the...
I think Cliff is ready to answer that if you want.
Well, I can just add this. If this is the case, or is this the kind of trajectory that one would fly if one were flying men around the moon?
Has he switched?
Yeah.
In terms of energy imparted to the trajectory, yes. In terms of the actual targeting, no. We're essentially shooting for a fictitious moon, so to speak. I don't know if anyone answered the question earlier, but we do not expect tomorrow for this trajectory to go around both the Earth and the Moon. We do not expect it to enter into the sphere of influence of the Moon.
This is Apollo Saturn Launch Control at T-minus 20 minutes and counting. Our countdown still proceeding at this time. In progress are a series of telemetry calibration checks, final calibrations of the overall telemetry system. This is done in an automatic manner using the computers here in the control center as well as the base computer below the vehicle at the launch pad. It's an automatic system of calibrating our telemetry systems to assure that we will get correct readouts in flight. A later report on weather looks very good. We have an expected temperature of about 70 degrees at launch time. Surface winds are down a little from our previous report. They're at about 12 knots with gusts at times up to 16 knots. The sky is very clear, very, very light cloud cover at very high altitude. We're also told that there'll be no problem with any high altitude winds on the mission attempt this morning. Still aiming toward a planned liftoff at 7 a.m. Eastern Standard Time. We just passed the 19-minute mark in our count. Now, T-minus 18 minutes, 55 seconds and counting. This is launch control.
Go ahead, George. I saw 3 more hands, and I'm afraid we're going to have to complete
George
it.
Alexander, Newsweek. Jack, any pilots in training, and if so, how many, and will they be watching it tomorrow?
We're supposed to be getting a list, George, of whatever astronauts will be here for the launch. I'll check on that as soon as this is over, and whatever information we have, we'll be glad to pass it on. We certainly, I certainly expect we'll have it by tomorrow morning. Go ahead, Tom.
I'd like to ask one question. What are the reasons, all the reasons, for the S-4B shooting for this fictitious moon target?
Well, you would exercise the antennas on the stage and find out whether you can communicate. That is, whether you receive signals or can send signals up and have them bounce back properly. That's certainly one very significant advantage. And then you would also find out whether you achieved your velocities you were looking for.
I hasten to add something so that there's no misconception. The S-4B has a guaranteed life of about 6 hours, and we hope that that'll go on to about 10 or 11 hours. As you heard earlier, this has a 15-day period, so we would only be able to get active signals back from the S-4B for those first 10 hours, not out at lunar distances.
Go ahead, Sue.
I would like to pursue Dick Lewis's question one step further. You said that the Saturn V is now rated for to lift 100,000 pounds. The present weight, the payload for tomorrow, comes to just under 94,000 pounds, according to the press information. However, this is only a 26,000 lunar test article. The real as I understand it, will be about 32,000, maybe more. If we add these 6,000, we will just barely make it with 100,000 pounds of payload in a vehicle capable of lifting 100,000 pounds. Isn't this very marginal? Maybe Mr. Lowe would like to answer.
So we do have a weight problem in Apollo. Command and service modules and the lunar module are essentially at the limit of weight that we can fly. We have the situation under control. The command and service modules have remained steady now at their current weight for the last 4 or 5 months. I'm talking about the command and service modules on the Block 2 vehicle that will be on the lunar mission. And we still have some margin left. The situation on the lunar module is somewhat tighter since we made the post-accident changes somewhat later, and we did not get the weights under control as quickly, but they too are leveling off now, and with very tight weight control and some possible weight reductions, I'm confident we're going to make it. But we are essentially at the limit, you're correct.
I'm afraid we're going to have to terminate the conference at this time. Thank you very much.
Apollo Saturn launch control at T-minus 15 minutes and counting. T-minus 15. At this point in the countdown, the Apollo spacecraft is now going to full internal power. We expect this will be coming up shortly. Of course, the main power system for the Apollo spacecraft are the fuel cells aboard. Up to this time in the count, we have been sharing the load, if you will, with the fuel cells with an external power source. At this point in the countdown, we remove the external power source, leaving us on the full power of the fuel cells themselves. Also, at this point, we start a chill down of the J2 engine in the third stage of the Saturn vehicle. That's the S4B stage. And we introduce some super cold helium into the chamber at this time at a temperature of some minus 300 degrees. This is to condition the chamber for that time in flight when the extremely cold liquid hydrogen and liquid oxygen will meet at ignition time for the third stage in flight. This chill down will continue down through the remainder of the countdown. We do a similar sequence with the S2, the second stage, those 5 engines in the second stage. This will come at the 8-minute mark in the count, once again to condition that chamber to prepare it for ignition in flight. Following are some of the highlights of the final phase of the countdown. We will go on an automatic sequencer at 3 minutes and 6 seconds in the countdown. From that point downward through ignition of those 5 engines of the Saturn V in the first stage, the countdown will be run automatically by the master computer here in the control center. However, during the last minute or so of the countdown, the 450-man crew here in the Launch Control Center will be monitoring some 350 or more than 350 parameters to assure that they are satisfactory. These are the so-called red line values in which we assure ourselves that the temperatures and the pressures aboard the vehicle are satisfactory for liftoff. If any of them are not, a hold could be called in the countdown. We'll be looking closely at temperatures concerned with the propellants on the second stage of the vehicle that have given us some concern. These will be watched closely during the final phases of the count. The ignition sequence on the first stage of the Saturn will begin at the 8.9 second mark in the countdown. This will be followed several seconds later by ignition of the 5 engines. This will occur at about the 6-second mark in the count, and in the span of 1/2 a second, all 5 engines should ignite. We will then start to build up thrust, get assurance that all engines are running satisfactorily at the 2-second mark in the count, and we will then get a commit at the 0 mark, assuring us that we have 90% of the thrust required for the Saturn V. This is in the area of some 7.5 million pounds of thrust. If we do get the commit from the automatic sequencer, those 4 hold-down arms will release, and the Saturn V will lift off on those 5 engines with some 7.5 million pounds of thrust. At ignition time, we'll have a vehicle on the pad standing 363 feet and weighing some 6.2 million pounds. During the early phases of flights, we'll have an inboard engine cutoff. That's the middle engine of the first stage. Will come at about 2 minutes and 23 seconds into the flight. The 4 outboard engines will cut off about 5 seconds thereafter, and this will be shortly followed by ignition of the 5 engines of the second stage. We'll have a burn of the S2 stage for some 6 minutes, followed by shutdown. Ignition then of the third stage. This would come 8 minutes and 43 seconds into the flight. On that first burn of the third stage will last some 2 minutes and 16 seconds and will insert us into a parking orbit. Following the 2 revolutions, and on the second pass here over the Cape, the third stage will be reignited. A burn time on this occasion of some 3 minutes and 10 seconds to give us the proper velocity required for the mission. The spacecraft will then separate. We'll have a burn a little later of the service propulsion system aboard the spacecraft. This will come some 3 hours and 20 minutes into the mission and will leave us with an apogee of some 12,000 nautical miles for the spacecraft. The overall mission for Apollo 6 is some 9 hours and 50 minutes. Shortly before we come back in, there'll be a second burn of the service module propulsion system, a 21,500-pound thrust engine, to give us a re-entry speeds and heating rates similar to those that would be encountered on a return from the moon. We're now approaching the 10-minute mark in the count. Mark, T-minus 10 minutes and counting. T-minus 10, and we are proceeding satisfactorily at this time. This is launch control.
At the beginning of the quarter, the second Saturn V flight vehicle stood fully erected in the Kennedy Space Center's Vehicle Assembly Building, with checkout underway for a scheduled launch next quarter. Checkout of the AS-502, which was developed under direction of the Marshall Space Flight Center, proceeded throughout December and January, with no major problems encountered. AS-502 will serve as launch vehicle for the Apollo 6 mission, an unmanned flight to qualify the Saturn V for future manned flights. Rollout of the 36-story tall space vehicle from the assembly building to Pad A of Launch Complex 39 was accomplished without incident on February 6th. The rollout operation, a 3-mile movement requiring some 7 hours, placed AS-502 in the launch position from which its predecessor, AS-501, began its successful flight last November 9th. The 502 mission will be essentially the same as that of the 501, evaluation of launch vehicle and spacecraft performance. AS-502 will carry several minor modifications directed by the Marshall Center as a result of data provided by the initial launch. Final updated versions of both the flight and ground program tapes for the computerized countdown and launch were delivered to KSC by the Marshall Center in early February. During the 10-hour Earth orbital Apollo 6 mission, a 5.5-minute S-4B stage second burn will duplicate that of an actual lunar mission. However, the Apollo spacecraft, after separation from the S-4B stage, will be limited to an apogee of 12,000 nautical miles by a 4-minute braking burn of its propulsion system. From its apogee, the spacecraft will simulate lunar mission return flight maneuvers, including a high-speed re-entry into Earth's atmosphere. The S-4B stage will travel about 279,000 miles into space on a 16-day elliptical Earth orbit. Due to the Moon's position at 502 launch, the stage will not actually swing around the Moon.
This is Apollo Saturn launch control at T-minus 7 minutes and counting. T-minus 7, all aspects of the mission still go at this time. Coming up in about a minute will be a final status check of the overall status to assure that we'll be ready for the flight of Apollo 6. We are standing by for further reports at 6 minutes, 40 seconds and counting. This is launch control. is Apollo Saturn Launch Control, T-minus 5 minutes and counting. T-minus 5. We've just completed our status check and all aspects of the mission are go. We received the final goes from Launch Director Rocco Petrone and Mission Director Bill Snyder. And just a matter of seconds ago, we received confirmation that the destruct system has been armed. The destruct system is armed and ready. We're now at T-minus 4 minutes and 35 seconds and counting. This is launch control.
It's 30 seconds and counting.
Saturn Launch Control, 3 minutes, 44 seconds and counting. Our countdown still going well, aiming toward our planned liftoff at 7 a.m. We're now a matter of about 20 seconds away from the automatic sequencer coming in. A matter of a minute or so ago, we retracted the cue ball cover, which protects the angle of attack meter atop the launch escape tower. Now 3 minutes, 25 seconds and counting. The terminal count sequencer is armed at the present time. The sequencer will come in at 3 minutes and 6 seconds, where the countdown will be completely automatic from that time down. 3 minutes, 10 seconds and counting. 3 minutes, 5 seconds and counting. We have firing command. The sequencer is in. T-minus 3 minutes and counting. Our countdown completely automatic from this time down. However, as reported earlier, the crew here will be monitoring a number of red line values to assure that we have satisfactory temperatures and pressures during these final moments of the count. Now, T-minus 2 minutes, 40 seconds and counting. The various propellant tanks within the Saturn V launch vehicle in all 3 stages are now being pressurized. They're primarily pressurized with helium to assure that we will get a good flow of both the liquid oxygen and the liquid hydrogen or the RP1 fuel, depending on the stage. T-minus 2 minutes, 20 seconds and counting. Our automatic status board here, driven by the computer, indicates all is still well with the countdown at this time. The pressurization sequence continuing, and we will stand by for further reports. Now coming up on 2 minutes. Mark, T-minus 2 minutes and counting. T-minus 2, we have confirmation that the second stage liquid oxygen tank now has been pressurized. 1 minute, 50 seconds and counting. All still going well at this time. One minute, 35 seconds. Still all going well at this time. The pressurization continuing within the Saturn V launch vehicle. 1 minute, 30 seconds and counting. All still going well at this time. Receiving some readouts on some of these red line values. All indications are that everything is still satisfactory. T-minus 1 minute, 15 seconds and counting. Third stage propellants now have been pressurized. This is launch control, T-minus 60 seconds and counting. First stage now pressurizing. We're coming up on the power transfer in a matter of seconds. This is when we switch to internal power aboard the vehicle. T-minus 50 seconds, we have the power transfer. The vehicle is internal. The complete vehicle is now pressurized. T-minus 40 seconds and counting. Our status board still indicates all is well. T-minus 35. T-minus 30 seconds and counting. Number 1 swing arm now being retracted from the Saturn V vehicle. 25 seconds and counting. T-minus 20, still counting at this time. T-minus 15, 14, 13, 12, 11, 10, 9. We have ignition sequence start. 6, 5, 4, 3, 2, 1, 0. We have commits. We have liftoff. Liftoff at 7 a.m. Eastern Standard Time. 5 seconds into the flight. We're looking good. We have cleared the tower.
Understand tower clearance. Houston Center assumes control. Pitch and roll program started. Our vehicle going now to an azimuth heading of 72 degrees. All 5 F1 engines firing. Looking good. Given a green light at this time from range safety. Roll program is completed now. Pitch profile still in progress. 40 seconds. Mark 45 seconds. Our vehicle well beyond the beach now. Our IP impact point moving out well over water as desired. Mark 56 seconds. Our cabin pressure is relieving, coming down now from a pad base 16 pounds per square inch. Looking good. Mark 1 minute, 10 seconds coming up on our period of maximum aerodynamic pressure on the vehicle. Still looking good. Mark 1 minute, 25 seconds. Pass through max Q. Still looking good. Now 10 nautical miles in altitude, heading out beyond the Earth's atmosphere. We're on our way. Mark 1 minute, 45 seconds, 14 nautical miles in altitude, 12 nautical miles downrange. Our velocity at this time, 4,600 feet per second and accelerating. Mark 2 minutes, Flight Director Cliff Charlesworth now polling members of his flight control team as to our status for staging, and we're standing by. Center engine has shut down. Our 4 outboard engines have shut down. Booster engineer reports ignition on our second stage. Our first stage will be falling away shortly now. It's day's work done. Again, the greatest weightlifting effort ever. Mark 2 minutes, 50 seconds, 40 nautical miles in altitude, 70 nautical miles downrange. Our interstage has separated this crucial timeline event right on schedule. Telemetry data intermittent at this time, standing by. Flight Dynamics reports our trajectory is go at this time. Bermuda has acquired our vehicle. The launch vehicle digital computer is now actively guiding our vehicle. Our pitch program, which slowly pitched our vehicle over about a half a degree per second, ended just before staging. We're now in iterative guidance mode 1, updating our heading every 2 seconds, and we're homing in for our target in space at this time. flight dynamics reports trajectory is go. Our vehicle now 80 nautical miles in altitude, 260 nautical miles downrange. Because of noisy data, we were not able to confirm tower jet as the event occurred. However, our trajectory looks very, very good at this time. Mark 5 minutes, 32 seconds. Our flight dynamics officer reports we have an S4B to orbit capability at this time. At this time, during the firing of our 5J2 engines, we're seeing a propellant ratio mix of our fueled oxidizer. This cutting the flow of oxidizer provides us with a higher specific impulse. Its effect much like the overdrive in a car for better gas mileage. Still looking good at 6 minutes into the flight. ECOM reports that it looks like we did get tower jet, again confirming tower jet. Mark 6 minutes 20 seconds, 92.5 nautical miles in altitude, 440 nautical miles downrange. We're at approximately 60% of our desired speed for orbit at this time. Mark 6 minutes 40 seconds. Our 5J2 engine still looking good. We should now be burning about 2,500 pounds of propellants per second. On the first stage, we expect we averaged about 29,000 pounds of propellants per second. Mark 7 minutes, still looking good. 96 nautical miles in altitude, 535 nautical miles downrange. Mark 7 minutes 20 seconds. ECOM reports our cabin pressure is now stable at 6 pounds per square inch, that desired for orbit. Mark 7 minutes 45 seconds. We have a preliminary report of a loss of 2 engines. This would be engines 2 and 3. However, our guidance is holding well and we're standing by. Our hydraulics are good, reports booster. We'll stand by for further confirmation of that report. This is only a preliminary report at this time. 8 minutes 10 seconds into the flight. Booster reports at this time are looking go. So we're standing by at 8 minutes 28 seconds into the flight. Our vehicle now 101 nautical miles in altitude, 780 nautical miles downrange. Booster reports our third stage looks good. We're at 8 minutes 52 seconds now into the flight. Our time delay for staging, apparently evidence of an engine out condition, but we're standing by for further confirmation. Mark 9 minutes 40 seconds, standing by. Our vehicle 105.7 nautical miles in altitude, 1,030 nautical miles downrange. Booster reports S4B ignition. Standing by. Flight Dynamics reports that trajectory confirms ignition. Booster reaffirms that our S4B is go at this time, now traveling 23,000 feet per second, approximately 90% of our desired speed in orbit. Looking good at this time, 10 minutes, 40 seconds of the flight of Apollo 6. Mark 10 minutes, 55 seconds. Guidance reports we have a predicted time of cutoff of 12 minutes, 19 seconds. Mark 11 minutes, 15 seconds. Our third stage is still go. We're reading 24,000 feet per second at this time. Our vehicle is moving on. Mark 11 minutes, 55 seconds. We're standing by. Mark 12 minutes, 15 seconds. Our predicted cutoff is moving out. It's 12 minutes, 33 seconds at this time, says guidance officer. Standing by. Our vehicle now 1,600 nautical miles downrange. Booster reports shutdown of our third stage. There's a small chair here in mission control. Our time base 5 clock is counting forward now. This is synced to the guidance program aboard the instrument unit in the launch vehicle. Fido says in very cheerful tones, we're go at this time. We're standing by now for Flight Dynamics to pass along our preliminary numbers in orbit. We're at 13 minutes, 25 seconds in the flight of Apollo 6. Reconfirming here that our third stage did shut down and we look good at this time. Our continuous vent valve aboard the third stage is open now, reports Booster. This is the vent which continuously vents hydrogen during our coast phase of orbit. Our first roll maneuver with the booster has initiated. If we had a crew aboard this morning, they would have been inserted into orbit in a heads-down position. This maneuver would effectively roll such a crew to a heads-up position. We're at 14 minutes, 29 seconds now into the flight of Apollo 6, continuing to look good. Our first maneuver by the booster has been performed in orbit. Mark 14 minutes, 50 seconds, still looking good. Our initial orbit report from Flight Dynamics indicates 193 nautical miles by 96. This taking into account our stretched out boost phase of flight. We will update those numbers as our flight progresses. We're now at 15 minutes, 30 seconds into the flight. Mark 17 minutes into the flight of Apollo 6 at this time. Our preliminary report of orbit numbers indicated that we had a high apogee. This no doubt accounted for by our long stretch out in the boost phase of flight. Initial orbit numbers reported by Flight Dynamics here in Mission Control were 193 nautical miles by 96 nautical miles. At 17 minutes, 35 seconds, this is Apollo Control Houston. This is Apollo Control Houston, 24 minutes, 16 seconds into the flight at this time of Apollo 6. We've had LOS with Canary at this time, our Apollo 6 vehicle over the west coast of Africa. Preliminary indications here in Mission Control indicate that we did in fact have an early shutdown of two of our second stage engines. This was sequenced in turn by a longer burn time on our third stage to bring us into orbit. Our shutdown stretching out some 2 minutes longer than had been anticipated in our flight planning. At the present time, our flight controllers here in Mission Control are surveying their data and evolving plans as to what impact this might have on our reignition of the third stage of the Saturn. We're standing by at this time for further updates and further reports, and at 25 minutes, 32 seconds into the flight of Apollo 6, this is Apollo Control Houston. This is Apollo Control Houston, 29 minutes, 8 seconds now into the flight of Apollo 6. Our Apollo 6 vehicle at this time is passing over the continent of Africa. We have an initial weight in orbit reading of some 264,055 pounds. This reduction in weight no doubt accounted for by our stretched out burn of the third stage single J2 engine. Again, our preliminary readings in orbit at this time, 195 nautical miles by 96 nautical miles. And we have a report that's come in from the Austin at Station 1 in the Atlantic. The Austin reports that one of the camera cassettes or capsules has been recovered, and that helicopters staging off of the Austin are homing in on two of the other camera cassettes. You'll recall that 6 camera cassettes are involved in this recovery exercise. We're at 30 minutes, 20 seconds now into the flight of Apollo 6. Discussions going on here in Mission Control, and this is Apollo Control Houston. This is Apollo Control Houston, 43 minutes. Our orbit numbers remain essentially unchanged, now reading 196 nautical miles by 96 nautical miles. Our vehicle at the present time is just passing out of range with Tananarive tracking. At this time, we have some preliminary numbers of our time sequences during the boost phase of flight. We had a reading here of liftoff at 1 second after the hour. Our first stage inboard engine cutoff in ground elapsed time was read at 2 minutes 24 seconds. Our 4 outboard engines shut down some 5 seconds later at 2 minutes 29 seconds ground elapsed time. We reported ignition on our second stage at 2 minutes 33 seconds. Our launch escape tower jettison time was in fact 3 minutes 7 seconds, very close to nominal. Our S2 engine cutoff was at 9 minutes 50 seconds ground elapsed time. This was the shutdown of all of the 5 J2 engines. Our earlier report indicated that S2 engines numbers 1 and 3, these are not adjacent engines, went out at approximately 7 minutes 37 seconds ground elapsed time. We had ignition on our third stage, single J2 engine, at 9 minutes 55 seconds ground elapsed time, and shutdown of our third stage engine at 12 minutes 31 seconds ground elapsed time. Almost 2 minutes longer than the time that had been planned in pre-flight. We're at 46 minutes 6 seconds now into the flight of Apollo 6, and this is Apollo Control Houston. This is Apollo Control Houston, 1 hour, 16 minutes, 25 seconds at this time into the flight of Apollo 6. Our Apollo 6 vehicle is presently passing over the Pacific out of range from any tracking stations, and will in fact be out of range until acquired during this, its first stateside pass. Our apogee at this time is reading 196.5 nautical miles. Our perigee is reading 97.1 nautical miles. Here in Mission Control at the present time, we're planning toward a second, third stage burn. Right now, the critical item being studied is the duration of this burn. Depending on how long the burn is will, of course, affect our apogees on both vehicles. Also on this will depend whether or not we do our first spacecraft service propulsion engine burn in a retrograde or a posigrade direction. Our initial plan, of course, was to have that burn following a pitch-over maneuver by the third stage in a retrograde direction. Preliminarily, we're looking at the start of what is known as Time Base 6. This is the guidance sequence within the instrument unit that begins the series of events leading toward the burn. This is presently being planned at 3 hours, 8 minutes, 3 seconds ground elapsed time, with an ignition time coming at 3 hours, 13 minutes, 30 seconds. These numbers, of course, will be updated as our planning continues. A correction to an earlier report, the 2 engines on the second stage, which appear to have shut down prematurely, were engines numbers 2 and 3, not 1 and 3 as previously reported. 2 and 3 are adjacent engines. We're now at 1 hour, 18 minutes, 35 seconds ground elapsed time, and this is Apollo Control Houston. This is Apollo Control Houston, 2 hours, 45 minutes, 47 seconds now into the flight of Apollo 6. Our Apollo 6 vehicle now passing over the western Pacific, out of reach of tracking stations at this time. Meanwhile, during the intervening period, our team of flight controllers here in Mission Control Center have been conferring with Marshall Space Flight Center personnel and feel reasonably assured that we have an excess of propellants available for the second S4B burn. Therefore, we do plan to go ahead with our restart, and mission plans according to what would be considered a normal mission. That is, in this case, we should have, assuming a nominal case, a burn duration of some 308 seconds, with ignition on the S4B occurring at 3 hours or 13 minutes 31 seconds ground elapsed time. A retrofire service propulsion system engine burn targeting for the 12,000 nautical mile apogee, and the second SPS burn to reentry. We estimate at this time we have some 320 seconds of available burn time on the S4B. With a guided cutoff, which we're targeting for with the S4B, this should lead us to our planned apogee of 279,000 nautical miles. Now, we've been following here what data indicates as a possible leak in one of our cold helium bottles associated with ullage engine pressures. The third stage, in this case, should not have a restart problem. However, it could cause an early shutdown coming at approximately 100 seconds into the burn time. However, we do expect to move ahead with our plans for the full duration burn. In the event of an early shutdown, we would expect the spacecraft to be separated and target towards a posigrade rather than a retrograde maneuver. Other times that we're looking at here in mission control at present, assuming a nominal mission, would give us a separation time of the spacecraft from the third stage and the spacecraft limb adapter of 3 hours, 21 minutes, 43 seconds ground elapsed time. Our first ignition on the service propulsion system engine of 3 hours, 23 minutes, 23 seconds, with an SPS-1 cutoff of 3 hours, 27 minutes, 37 seconds. We expect these times to be updated as we proceed towards what is known as time base 6. We're at 2 hours, 49 minutes, 6 seconds into the flight of Apollo 6, and this is Apollo Control Houston. This is Apollo Control Houston, 3 hours, 5 minutes, 20 seconds now into the flight of Apollo 6. Our vehicle coming up now on its second stateside pass, leading to the reignition of the S4B engine. Just prior to the start of our time base 6, in fact, right now, our S4B engine is undergoing what is referred to as a chill-down process. Here, the propellants are circulated through the engine plumbing to condition against a thermal shock. If there was a difference in temperature, if these lines were too long or too warm, it could create a gas pocket and stop the propellant flow. It's an important procedure, and we will do it twice. We're doing it now, and we will do it again after the time base 6 sequence begins. We've had a later report from Booster that our helium pressure situation looks very favorable at this time. We can do the full duration burn with some 500 psi, and it appears at the present time that we have in excess of 800 psi. Very favorable at this time, but we'll stand by for updates. We're at 3 hours, 6 minutes, 40 seconds. This is Apollo Control Houston. We've just started our time-based 6 sequence. 3 hours, 8 minutes, 24 seconds now into the flight. Continuing to monitor in Mission Control Houston. Our continuous vent valve has been closed. We have an update on our ignition time from guidance of 3 hours, 13 minutes, 34 seconds. This is Apollo Control Houston, 3 hours, 9 minutes, 53 seconds. Continuing to monitor here in Mission Control. Still targeting toward our reignition of the third stage at 3 hours, 13 minutes, 34 seconds and standing by. Our liquid oxygen tank repressurization has been initiated. Three hours, 11 minutes. Standing by. Our restart maneuver has been initiated. Our vehicle, just prior to burn, will go to a slight pitch-up attitude. Three hours, 11 minutes, 54 seconds. Our liquid hydrogen tank repress has been initiated. This is Apollo Control Houston, 3 hours, 12 minutes, 35 seconds. Booster reports he looks good at this time. We're at restart attitude at this time. Guidance looks good at this time, 3 hours, 12 minutes, 55 seconds. Less than a minute away now from our reignition time. Less than or about 30 seconds away now from our reignition time. Apollo Control Houston, standing by. No confirmation on ignition at this time, standing by. Standing by at this time. Three hours, 14 minutes. 20 seconds. Still no report of an ignition. Standing by for a separation command. We have a report of adapter SEP, a real-time command 71 being sent. Three hours, 14 minutes, 52 seconds. We did not have reignition on our third stage engine. We have sent a real-time command, number 71, to separate from our vehicle. We're standing by for further updates. We're in an ignition attitude now on our spacecraft at the present time, standing by. Standing by for the first burn of our service propulsion system engine. Standing by for our service propulsion system burn. SPS is on. Our flight dynamics officer confirms ignition on our service propulsion system engine. Guidance says we're looking good at this time on this burn. Standing by. Engine is looking good. Still looking good on SPS-1. Uh, 3 hours, 16 minutes, 55 seconds, standing by for an estimate on our duration of burn. This is Apollo Control, Houston. We have a preliminary estimate on our burn time of 7 minutes, 24 seconds. Quite a long burn. We'll stand by. We report an apogee at this time of 1,000 nautical miles and coming up. This is Apollo Control, Houston, 3 hours, 18 minutes, 20 seconds, continuing with our service propulsion system engine burn. Report here that our vehicle looks very stable. 3 hours, 18 minutes, 35 seconds, continuing to monitor our service propulsion system engine 1 burn. Apogee climbing, now 1,600 nautical miles. I report our apogee is now 2,000 nautical miles and continuing to climb upward. Still looking good, 3 hours, 19 minutes, 45 seconds as we continue with our service propulsion system engine number 1 burn. This is Apollo Control, Houston, 3 hours, 20 minutes, 15 seconds, still on SPS number 1. This burn of some 7 minutes, 24 seconds in duration, this the time anticipated. Antigua has our spacecraft under acquisition at the present time. We're at 3 hours, 20 minutes, 40 seconds into the flight of Apollo 6. Still looking very good on this SPS burn. Our apogee has now risen to in excess of 4,300 nautical miles. Our perigee coming down for the desired Earth intercepting orbit. It's now down to 77 nautical miles. 3 hours, 21 minutes, 50 seconds. Continuing with our SPS burn. Apogee reported at 6,000 nautical miles at the present time. Perigee now down to 60, coming down nicely as desired. Our velocity reading at the present time some 30,720 feet per second, and going up. Apogee 8,800 nautical miles, perigee holding about 40, looking good. Less than 10 seconds anticipated on our burn duration at this time. Reported our service propulsion system engine is off. We're standing by. And it looks like we're right on the money. Our spacecraft at the present time is maneuvering to its cold soak attitude. This will put the Apollo spacecraft essentially in a tail to the sun position, the SPS engine to the sun. This allows for a maximum cold effect on our heat shield. It should provide temperature ranges of perhaps minus 150 degrees Fahrenheit on our command module heat shield. We're standing by at the present time for further updates on our orbital numbers as well as burn duration, and we'll pass those along as soon as they become available. At 3 hours, 24 minutes, 38 seconds into the flight of Apollo 6, this is Apollo Control Houston, continuing to monitor. This is Apollo Control Houston, 3 hours, 30 minutes, 8 seconds now into the flight of Apollo 6. Program 24 has begun, which effectively our computer is asleep for this, the cold soak period. We still have no definite indication or no indication as to why we did not get reignition on our third stage. However, as we quickly followed the data here, the instrument unit sequenced into time base 7, which effectively tells us that the burn should have ended. This put us in a position of sending the separation command, which was done, and we had a very healthy burn on our service propulsion system engine. We will stand by, continue to monitor, and provide updates as they become available. At the present time, it appears that our service propulsion system engine number 2 burn, this is the second shortly before reentry, will be a burn to fuel depletion, but we will refine those numbers. This is Apollo Control, Houston. This is Apollo Control Houston, 3 hours, 36 minutes, 49 seconds now into the flight of Apollo 6. We have preliminary readings on our orbital numbers on the spacecraft at the present time. As of this time, we indicate an apogee reading of 12,028 nautical miles and a perigee reading of 0. Our spacecraft at the present time is under acquisition by Ascension Tracking Station in the Atlantic. Also, numbers passed along to us indicate that our separation occurred at 3 hours, 14 minutes, 25 seconds ground elapsed time, with SPS-1, Service Propulsion System Engine number 1 ignition, occurring at 3 hours, 16 minutes, 5 seconds, and the SPS-1 Cut-off or Shutdown occurring at 3 hours, 23 minutes, 23 seconds. At the present time, discussions are underway here in Mission Control as to what we should do, if anything, further with the booster. We're at 3 hours, 37 minutes, 58 seconds now into the flight of Apollo 6, and this is Apollo Control Houston. This is Apollo Control Houston at 3 hours, 57 minutes, 20 seconds into the flight of Apollo 6. Our Apollo 6 spacecraft at this time passing over the coast of southern Africa out of range of our tracking stations. Let's go over again some of the events as they rapidly occurred as we entered into time base 6, the time base and the instrument unit which would lead up to reignition of the S4B. We did not, did not get ignition on our S4B third stage. The launch vehicle sequenced into a time base 7, which tells the IU that our S4B has in fact shut down. From here, we followed one of our alternate mission plans, specifically the alternate mission plan for this case. A separation command was sent from the Mission Control Center in Houston, and the spacecraft command and service module separated from the spacecraft limb adapter attached to the S4B. From here, the spacecraft burned posigrade, and this burn duration some 7 minutes, 21 seconds. To an apogee of 12,019.1 nautical miles. Our current perigee reading is 0 nautical miles, which gives us our desired Earth intercepting orbit. Right now in Mission Control, we're discussing what to do further with the booster, if anything, in the way of tests. No decision has been made as yet regarding this matter. We have an estimated 23 seconds of burn time remaining on our service propulsion system engine on the spacecraft. Right now, under consideration is whether or not to go for our second service propulsion system engine burn, which would be a burn to fuel depletion, or to accept our parameters, which will bring about a desired reentry. Our mission duration that we're looking at, because of our orbit numbers, should be about the same as that pre-planned, also with a Pacific landing on the spacecraft. We're at 3 hours, 59 minutes, 56 seconds into the flight of Apollo 6, continuing to monitor, and this is Apollo Control Houston. This is Apollo Control, Houston. 4 hours, 27 minutes, 10 seconds now into the flight of Apollo 6. Our Apollo 6 spacecraft continuing at the present time in its long, high coast period with the cold soak associated with this. At the present time, we read our spacecraft altitude in excess of 7,200 nautical miles. We're looking at an apogee, as you'll recall, of 12,019.1 nautical miles. A decision has been made here in Mission Control Center not to continue or to proceed with our second service propulsion system engine burn. This decision was made on primarily on the factors that by doing the burn would provide only a small addition of energy. You'll recall that we have 23 seconds of fuel time remaining on the service propulsion system engine. Also, it is of the two alternates, it's considered less desirable to burn to a fuel depletion. Because of this, our re-entry point or impact point should be somewhere in excess of 200 nautical miles short of that planned for a nominal mission. Because of this, we're moving our ship, the Okinawa, and it's proceeded with its move. We do not expect to cover the full range of this 220 nautical miles during this time frame, but we would expect the Okinawa to be some 100 to 110 nautical miles away from the spacecraft at time of splash. To provide our necessary recovery, the helicopters will be deployed as planned, and we expect a 130 type aircraft overhead. We're at 4 hours, 29 minutes, 40 seconds in the flight of Apollo 6, continuing to monitor during this, our cold soak period. This is Apollo Control, Houston. This is Apollo Control, Houston. 5 hours, 7 minutes, 15 seconds now into the flight of Apollo 6. Our Apollo 6 command and service module now just under 10,000 nautical miles in apogee, continuing to move upward towards its projected 12,019.4 nautical mile apogee. A relatively quiet time here in Mission Control Center, unlike some of the periods earlier this morning, as our flight control team is planning towards our entry phase of the flight. We still have no definite or no indication as to why we did not get a reignition on our third stage engine. We're at 5 hours, 8 minutes, 12 seconds into the flight of Apollo 6, and this is Apollo Control, Houston. This is Apollo Control Houston, 5 hours, 46 minutes, 25 seconds now into the flight of Apollo 6. Our Apollo 6 spacecraft on our world map displays appearing almost static in its geographical location to the south of Tananarive tracking station. However, high above Tananarive tracking station our spacecraft is at the present time. At the present time we have an altitude reading of 11,481.2 nautical miles. As it is at the last lap of its uphill climb, we note our velocity in feet per second on the vehicle trimmed down considerably. Our current velocity reading 8,081 feet per second. We're still looking for what should be a near nominal mission time, somewhere slightly under 10 hours in duration. We're continuing to monitor. It's relatively quiet in mission control at the present time. We're at 5 hours, 47 minutes, 42 seconds, and this is Apollo Control Houston. This is Apollo Control Houston at 6 hours, 23 minutes, 2 seconds now into the flight of Apollo 6. Geographically, our spacecraft continues to hover just to the south of Tananarive. We should be very close at this time to our point of apogee. We have a feet per second velocity reading at the present of 74.15. Our feet per second inertial velocity predicted prior to the flight at apogee was in fact 74.15. Our current altitude reading 12,010.9 nautical miles and updating itself. And at 6 hours, 23 minutes, 58 seconds into the flight of Apollo 6, still in a period of quiet planning and mission control, and this is Apollo Control Houston. This is Apollo Control Houston at 7 hours, 7 minutes, 54 seconds now into the flight of Apollo 6. Our Apollo 6 spacecraft now coming down the backside of its high apogee. We have an altitude reading at the present time of 11,500 nautical miles. We have some very preliminary numbers at the present for our end of mission time sequences. We're looking at a ground elapsed time for re-entry in the atmosphere of 9 hours, 38 minutes, 24 seconds. We're looking at a time of blackout begin at 9 hours, 39 minutes, 6 seconds. End of blackout at 9 hours, 40 minutes, 37 seconds. Main chute deploy 9 hours, 43 minutes, 31 seconds. And our early prediction of a splash time of 9 hours, 48 minutes, 31 seconds. We're continuing to monitor at the present time in mission control, and this is Apollo Control Houston. This is Apollo Control Houston at 7 hours, 33 minutes, 45 seconds now into the flight of Apollo 6. Our Apollo 6 spacecraft continuing to descend from its earlier high position. We currently read an altitude of 10,727.6 nautical miles. Our velocity beginning to build up. We're reading at the present time some 9,072 feet per second. This will extend out at an increasingly rapid rate as we continue with our descent. As we had reported earlier, we do not plan a second service propulsion system engine burn. Our fuel remaining was some 23 seconds. We have chosen not to make that burn because we had our desired Earth intersecting orbit. A report from the Austin. We have recovered 2 of the camera cassettes and have discontinued the search on the remaining 4. Hilo is due to leave the Austin at first light tomorrow morning to return the cassettes to Cape Kennedy, or Patrick Air Force Base. At the present time, we're looking at a very preliminary predicted IP point. This position being 27 degrees 19 minutes west, 157 degrees. Correction here, that's 27 degrees 19 minutes north, 157 degrees 11 minutes west. This some 270 nautical miles short of our pre-mission planned IP. We'll stand by for further updates. We're at 7 hours 35 minutes 56 seconds, and this is Apollo Control Houston. This is Apollo Control Houston at 7 hours 46 minutes 13 seconds into the flight of Apollo 6. We have a correction to make to an earlier report on our predicted coordinates at this time for splash. The coordinates which we read to you were pre-mission coordinates. What we're looking at the present time is 28 degrees 57 minutes north, 162.52 minutes west. The earlier coordinates which were passed along were those calculated pre-mission. We're at 7 hours 46 minutes 58 seconds into the flight of Apollo 6, and this is Apollo Control Houston. This is Apollo Control Houston at 8 hours 48 seconds into the flight of Apollo 6 at the present time. We have some further updated re-entry ground elapsed times to pass along. These, of course, subject to change as our mission progresses. At the present time, we're looking at time of entry at 9 hours 38 minutes 24 seconds. Time of blackout begin 9 hours 39 minutes 6 seconds. Time of blackout to end 9 hours 41 minutes 9 seconds. Time of main deploy 9 hours 50 minutes 36 seconds. Time of splash 9 hours, 56 minutes, 3 seconds. These numbers based on an entry with our primary system, the guidance and navigation system. Our coordinates remained essentially unchanged from those that we had earlier reported. At the present time, our spacecraft continuing to come down, our velocity continuing to go up. We currently read a velocity of 10,909 feet per second. Our altitude at this time approximately 9,000 nautical miles. We're at 8 hours, 2 minutes, 35 seconds, continuing with our downward trek in Apollo 6, and this is Apollo Control Houston. This is Apollo Control Houston at 8 hours, 29 minutes, 18 seconds into the flight of Apollo 6. Our Apollo 6 spacecraft at the present time continuing on its downward track. Velocity increasing, now reading 13,600 feet per second. We have an update on our third stage of the S4B, which is still in orbit. Our current orbit reading on this, the third stage, is 213 nautical miles by 107 nautical miles. We have a predicted battery lifetime on our instrument unit of between 10 to 11 hours since liftoff. Some 2 hours or so away from this time. We are continuing to track the vehicle at the present time, and will continue to do so as long as the battery lifetime holds out. At 8 hours, 30 minutes, 27 seconds into the flight of Apollo 6, this is Apollo Control Houston. This is Apollo Control Houston, 8 hours, 50 minutes, 3 seconds now into the flight of Apollo 6. Our Apollo 6 spacecraft continuing its downward descent at this time. At this time we read an altitude of 5,410 nautical miles and coming down. At time of predicted splashdown, the ground elapsed time that we're going with at present, of 9 hours, 56 minutes, 3 seconds. We expect the Okinawa to be some 170 nautical miles away from our predicted point of splash. Deploying from the Okinawa will be 5 helicopters. This would include 3 rescue craft, 1 with swimmers, 1 search helicopter, with no swimmers aboard but to aid in the search, and 1 communications relay helicopter. The Okinawa itself will be some 4.5 hours away from our predicted point of splash, and this with some 2.5 hours of daylight remaining. Our positioning in the helicopters, 2 of the recovery helicopters will be 110 nautical miles downrange from the Okinawa, and the 3rd recovery helicopter will be some 50 nautical miles away from the Okinawa at about a 60-degree arc. That would be a downward arc. An upward arc would be our search helicopter, the one with no swimmers aboard. This some 50 nautical miles away from the Okinawa. Also in the area, we will have 6 HC-130s. These on either side of track. Decision to deploy swimmers will be based, of course, on readouts by our aircraft commanders, the Okinawa, and our recovery people here in the Mission Control Center. We'll stand by for further updates at this time, and at 8 hours, 52 minutes, 40 seconds, this is Apollo Control Houston. This is Apollo Control Houston, 9 hours, 40 seconds now into the flight of Apollo 6. Continuing with our spacecraft descent, we're now at 4,200 nautical miles in altitude and continuing to descend. In the recovery area at the present time, we forecast a weather of with clouds of 2,000 feet and scattered, visibility of 10 nautical miles, winds of 70 degrees in direction, and 15 knots. We expect 5-foot wave heights. Also in the area and standing by on each side of track are 2 Apollo range and instrumentation aircraft. We're at 9 hours, 1 minute, 32 seconds into the flight of Apollo 6 and standing by. This is Apollo Control Houston. This is Apollo Control Houston, 9 hours, 15 minutes, 12 seconds now into the flight of Apollo 6. Our spacecraft computer, has been awakened, and we expect a verification momentarily as to our navigational update into the computer. As we continue our downward plot, we're now at 2,400 nautical miles. Our velocity continuing to build upwards, 23,356 feet per second. Our navigational update is confirmed as being incorporated, and we're standing by at 9 hours, 15 minutes, 59 seconds into the flight of Apollo 6. This is Apollo Control Houston, 9 hours, 29 minutes, 52 seconds into the flight of Apollo 6. At the present time, coming in as programmed, our altitude at this time, 682 nautical miles. Our velocity building up, we're reading at the present time 29,740 feet per second. We anticipate at the present time a command service module separation of 9 hours, 37 minutes, 50 seconds, this some 7 minutes from this time, and we're standing by. This is Apollo Control Houston. This is Apollo Control Houston, 9 hours, 35 minutes, 8 seconds. Our guidance officer has just reported we've started program 61. This is to maneuver our spacecraft to a separation attitude. And our maneuver appears nominal at the time, indicating that our command and service module is maneuvering to the correct separation attitude. Meanwhile, we're looking at updates on our re-entry timeline profile. We're now reading ground elapsed time for entry interface of 9 hours, 38 minutes, 23 seconds. Time of start blackout, 9 hours, 39 minutes, 5 seconds. Start of end blackout, 9 hours, 41 minutes, 6 seconds. Time of main deploy, 9 hours, 50 minutes, 41 seconds. And time of splash, 9 hours, 56 minutes, 8 seconds. We're at 9 hours, 36 minutes, 15 seconds, and we're standing by. This is Apollo Control Houston, 9 hours, 37 minutes, 7 seconds. We've had LOS with Guam. Watertown has acquired the spacecraft, and they confirm CM-SM separation at this time. We're standing by for further updates at 9 hours, 37 minutes, 24 seconds. This is Apollo Control Houston, 9 hours, 37 minutes, 55 seconds. Our separation has occurred. We're now in GNN entry mode, program 62, maneuvering to a proper entry attitude. We're standing by. This is Apollo Control Houston, 9 hours, 38 minutes, 48 seconds into the flight of Apollo 6. Our bottom clock to the right of our display area here in Mission Control is now counting down to splash. Some 17 minutes, 35 seconds away at this time. This is Apollo Control Houston, 9 hours, 39 minutes, 36 seconds into the flight. At this time, we should be in our period of blackout, and we're standing by. This is Apollo Control Houston, 9 hours, 40 minutes, 33 seconds, continuing to stand by and monitor at this time. This is Apollo Control Houston, 9 hours, 41 minutes, 24 seconds. We're some 15 minutes away from predicted time of splash at this time and continuing to monitor. This is Apollo Control Houston, 9 hours, 44 minutes, 5 seconds. Now into the flight of Apollo 6. We've just received a report that the destroyer Carpenter had radar contact with our spacecraft and had both acquisition of signal and loss of signal, indicating that we're passing by the Carpenter. This is Apollo Control Houston, 9 hours 46 minutes 40 seconds. We're some 4 minutes away from a time of main chute deploy, and some 9 minutes 46 seconds away from predicted time of splash. Standing by, this is Apollo Control Houston. Apollo Control Houston, 9 hours 47 minutes 12 seconds. Just received a report here that one of our Apollo range and instrumentation aircraft has acquisition of signal on our spacecraft. Standing by. This is Apollo Control Houston. A report here that our Rescue 4 aircraft has S-band contact with our spacecraft on the other side of our period of blackout. And we're standing by, 9 hours 48 minutes 43 seconds. Further report here that Hawaii Rescue 6, the HC-130, has also acquired S-band contact with our spacecraft. This, the rescue aircraft that's the furthest downrange. Apollo Control Houston, some 6 minutes 57 seconds away from our predicted time of splash. Standing by. This is Apollo Control Houston, 9 hours 50 minutes 7 seconds. Some 6 minutes 25 seconds away from predicted time of splash. Standing by for a confirmation on our chute deploy when we can so report. Apollo Control Houston, 9 hours 51 minutes. All of our aircraft, recovery aircraft on station, standing by, continuing to monitor at this time. This is Apollo Control Houston, 9 hours 52 minutes, and standing by at this time. We're some 4 minutes 18 seconds away from our predicted time of splash. This is Apollo Control Houston, 9 hours 54 minutes, 5 seconds. We've just received a report that Hawaii Rescue 5 is acquired the beacon on the main chute, indicating that we have deployed our chute. Standing by at 9 hours 54 minutes, 23 seconds. I'm not... Further update here, Hawaii Rescue 6 also has a bearing on our beacon, indicating too that it is looking at confirmation of main chute deploy. Apollo Control Houston, our report from Rescue 6 would indicate that we might be a bit downrange from our predicted impact point. We're standing by for further updates. This is Apollo Control Houston. We should be coming up just about now on our predicted time of splash, and we're standing by for further updates. This is Apollo Control Houston. We've just received a report here that our Ariya 1 aircraft has visual contact with the spacecraft. And coordinates passed along were 161 degrees, 13 minutes west, and 31 degrees, 21 minutes, or 30 degrees, 21 minutes north. We're standing by at this time for further updates. That was our Apollo range and instrumentation aircraft, which was located on station north of our track. We're standing by. This is Apollo Control Houston. The set of coordinates just passed along would place our spacecraft some 75 nautical miles southwest of the Okinawa, which is closer in than we had earlier anticipated. We'll stand by. This is Apollo Control, Houston. We've just received an indication that a beacon report from one of our rescue aircraft would tend to confirm the visual sighting of our Arrival. This is Apollo Control, Houston. We had a clarifying report from our Arrival 1 aircraft, which indicated it was an electronic and not a visual contact. Standing by. This is Apollo Control, Houston. We received a preliminary report that Hawaii Rescue 6 is now below the clouds and homing in on the beacon on the spacecraft. Further indication that we had a true heading of 93 degrees. This would be almost due east, and 77 nautical miles from our Okinawa. Standing by for further updates at this time. This is Apollo Control, Houston. This is Apollo Control, Houston. We've just received a report that Hawaii Rescue 6, which has been homing in on our spacecraft, has a visual contact at this time. We're standing by for further updates. This is Apollo Control, Houston. It's been passed along to us that the pilot of the Hawaii 6 rescue aircraft is Captain James Clark. His hometown, Pittsburgh, Wisconsin. Standing by at this time. This is Apollo Control, Houston. This is Apollo Control, Houston. We have a preliminary set of coordinates passed on based on this visual position report from Hawaii Rescue 6. These coordinates that we're looking at the present time, 27 degrees 40 minutes north, 57 degrees 55 minutes west. Quite close to our nominal IP before the mission. Standing by for further updates. This is Apollo Control, Houston. This is Apollo Control, Houston. We have a report that our spacecraft is some 80 nautical miles away from the Okinawa. Some 4 hours away from the Okinawa at this time. This is Apollo Control, Houston. Apollo Control, Houston. We have a report here that we should have a helicopter over the spacecraft in about 37 minutes. This, of course, would have swimmers aboard, and we're standing by at this time for updates. This is Apollo Control, Houston. We've had a report from Hawaii 6 reporting that our spacecraft is floating normally in the water. We have no chutes in sight at this time. Standing by. This is Apollo Control, Houston.
We're reacting to some 12 hours worth of hard work. It was a good job all around, an excellent launch, and on balance, a most successful mission. This in spite of the fact that we had two major problems during the course of the flight. Our object in these flights, as you know, is to learn what we need to learn in order to go to the moon safely. And in that context, we have learned a great deal today. I'd like to recap just briefly some of the events. Again, we had an on-time launch, the second Saturn V launch, and the second one within 1 second of the planned launch time. The S1C stage, of course, operated successfully. I think it's particularly appropriate to notice the quick and positive action that was taken in connection with the decision to separate and fire the service module propulsion system. The spacecraft performance was successful for the fourth time, and we have, of course, gained again an invaluable increment in our understanding of how to launch and prepare these Saturn V's for launch. On the negative side, as you know, we launched today, actually almost 1 month to the day from the time we had originally planned last year to launch this Saturn V02. We had two major problems during the course of the launch. One was the premature shutdown of the engines on the S2 stage, and the second was the failure of the S4B stage to reignite. We will be examining the data from the launch over the next several weeks, and we will be going through the process that is required before we make a decision as to where we go from here in the program, and in particular, it will be several weeks before we make a decision as to whether or not Saturn 503 will be flown as an unmanned test vehicle. As this particular flight is in many respects similar to that of our first unmanned LEM flight, where over a period of time we examined the results of that flight and concluded that we had met the primary objectives of that LEM-1 mission. I've been going through the mission objectives that we established for Apollo 6, and of the primary objectives, we met 4 out of the 5 completely. One was partially complete because we did, in fact, fire the S2 stage successfully. We did successfully achieve orbit in spite of the malfunction of those 2 stages. We would have been able to successfully carry out the lunar mission in this particular instance if the S4B stage had reignited. Second thing, of course, that was not successfully completed was the second burn of the S4B. The first burn was quite successful. In looking at our detailed test objectives, I note that we made 13 out of 16 completely successfully in the launch vehicle area. One we missed completely, and 2 were partially met. And I think those are that's sort of the balance sheet for the meeting of our objectives with respect to the launch vehicle. As you know, the spacecraft was not a primary objective of this meeting, of this particular mission. The emergency detection system was. It did perform successfully. So that we did meet that primary objective of the spacecraft itself. With that, I think I'd like to turn it over to Sam Phillips to give you the details of the S4B and S2 and the flight itself. Sam?
Thank you, George. I'll discuss briefly the facts, as they are known at this time, concerning the 2 significant malfunctions that did occur on the launch vehicle in this Apollo 6 flight. The first of these, the shutdown of 2 of the 5 engines on the S2 stage. I think the significant points of fact and data available at this time are these. At 27 seconds into the S2 stage operation, the second plane separation occurred at the proper time and as planned. There is a visual observation that the separation of this skirt or interstage
appeared to be different visually than the appearance visually on 501. Now, that may or may not be significant at this point in time, but since it was a reported observation, I wanted to bring it out. We have arranged for expedited processing of the film from the camera that was recovered in the one cassette that was carried aboard the S2 stage to observe this this stage skirt separation. That will be prepared and studied as rapidly as we can sometime tomorrow. At about 2 minutes and 47 seconds into the S2 stage operation, the data indicates that there was a 30 psi drop in the chamber pressure of the number 2 engine. At 4 minutes and 21 seconds into the S2 operation, the number 2 engine start tank pressure decayed. About 0.2 of a second later, engine number 2, liquid hydrogen and liquid oxygen, engine inlet pressures dropped. This was followed a half a second later by engine number 2 cutoff. So this was the point of shutdown of the first of the 2 engines, engine number 2. So that's at 4:21.7. 1 second later, engine number 3 shut off.
Pardon me, Sam, would you read those times again to us, please?
Second plane separation was at 27 seconds. The time base here is the S2 start. 30 psi pressure drop, number 2. Engine chamber pressure, 2 minutes and 47 seconds. Number 2 engine start tank pressure decayed, 4 minutes and 21 seconds. 0.2 of a second later, the propellant inlet pressures in engine number 2 dropped. Half second later, engine number 2 cut off. 1 second later, engine number 3 cut off, and simultaneously there was observed a heavy current surge on the instrumentation bus. Let me correct that latter point. The 50 amp surge, the heavy current surge on the instrumentation bus, occurred simultaneously with the cutoff of number 2 engine, the first of the 2 that cut off. Almost immediately with the, almost simultaneously with the shutdown of number 3 engine, the second one to shut down, we lost several measurements. They had to do with indicating position of gimbals and with temperatures and so on. So there was quite a loss of instrumentation in the S2 stage area. Now, about a minute later, a minute later than what I've just given you, the step change of the mixture ratio occurred, and that occurred at the time it was planned. And so it occurred after these engine shutdowns, and I think makes improbable the cause that we were suggesting this morning as one of the possible causes. In other words, a correlation with the propellant utilization mixture ratio shift. So that correlation would appear now to no longer be a suspect. I think that gives you the essential facts on the S2. Let me briefly give you the essential facts on the S4B. The S4B operation during the first burn was normal. You'll take account here that the burn was some seconds longer than the nominal mission plan because it was called upon to make up some velocity deficiency that had occurred because of the 2 engines out on the second stage. The data indicates that the helium spheres that are there to provide pressurization for the propellant tanks were decaying in pressure. The numbers aren't in yet. The
helium pressure did stabilize, however, and the best number I have so far is that it stabilized at approximately 1,200 psi, which is presently believed to not be a factor in the failure to start, because the pressure was adequate to provide the tank pressures necessary for start. The data indicates that the auxiliary hydraulic pump was commanded on but did not come on. Later in the mission, after the spacecraft had separated, it was commanded on 2 more times and did not come on. Now, whether that's significant in the failure to start hasn't really been evaluated, but it's a fact, and I pointed out here. At the start of the S4B, the data indicates that the engine start conditions were normal, that the pressures, temperatures, valve positions had been established as necessary to start this engine. The data indicates that the ignition command was sent at the proper time. The data indicates that there was the necessary voltage and current to the igniter. There is, however, no evidence of ignition. The gas generator, which is providing gas to operate the propellant drive pumps, came up, did spin up, and served its function. However, the pressure in the engine chamber reached, and the reported figure so far is a maximum value of 40 pounds per square inch in this ignition time period, when it should normally have achieved a pressure of about 200 psi at that time. Now, that indicates, that plus the other indications that have been looked at so far indicates that there was not an ignition. There is no evidence, in other words, that the engine actually ignited. The igniter in the engine is redundant. In other words, there are 2. And as I've said, the data indicates that it got its signal and that the proper voltage and current applied. The facts don't so far give a conclusive reason for the failure to start. Now, let me conclude by remarking that it's necessary that we understand completely why both of these malfunctions occurred, that we understand and evaluate fully the corrective action that's necessary to ensure that these malfunctions will not occur on any other Saturn V's. The method by which these corrections will be tested remains to be established when we have understood the failure and the necessary corrective action. By that I mean, I see ahead several days of very hard work to gather and evaluate the data to establish the facts and the corrective action and the testing required to evaluate those fixes. And in considering the testing necessary, we will certainly be considering the full range of our ground test program, as well as the question of flying the 503 Saturn V on the unmanned flight for which it is currently being prepared. That decision has not been made. It will not be made immediately. There are several days of hard work ahead to understand this situation and to consider that in relation to the need in the progress of the program to fly 503 unmanned. And that may turn out to be the decision. It may not, after all the facts are fully evaluated. The concluding point I'd like to make is that there were, in the course of these malfunction operations today, one thing that I think is significant to the future of our program was clearly demonstrated, namely that these substantial malfunctions that altered significantly the course of the mission failed in a safe way. And I think that's something that we've been striving as a design objective to keep in mind where possible is to prevent failures through all manner of full development, but to keep in mind a design objective of fail-safe. Well, the facts will tell us perhaps or probably why, but it is significant, I think, that these were non-catastrophic, significant malfunctions, and I think that will have a bearing on the future of attaining our further objectives in Apollo. Thank you.
Thank you, General. Well, we'll now switch to Houston at this time.
It was a fine day for the spacecraft. All the systems performed well. We had an excellent test of the service propulsion engine in the initial burn right after separation from the S4B, and all other systems performed well. I personally am proud of all the participants, from George Lowe and his spacecraft team to Chris Kraft, his operations team, and the DoD forces, recovery forces headed by General Houston. We have all the key participants, representatives of them here at this end, and I think it's an excellent suggestion to have Mr. Charlesworth summarize the events up to recovery, and then I think General Houston will summarize the recovery efforts.
I guess I can begin with a statement that it was an interesting day from our point of view. We had a number of problems, but I think we were prepared for the problems that we experienced. The pre-planning that we had done, nothing caught us completely by surprise that we weren't prepared to handle. I was particularly pleased with the performance of our manned spaceflight network. This is the first time we've flown completely remoted, that is, with no controllers around the world. We did experience some minor problems, as you would expect the first time out. However, we were able to work around them on the network and did not have any significant loss of data in Houston. I would also like to express my appreciation and compliments to all of the people that go into this flight control team. You hear a lot of the people in the control center itself, but there are a lot of people that put in the work and the effort to prepare alternate mission plans and predetermine the course of action we should take. I think all of this paid off today. We were able to adjust to the situations that we had and press on and get most of our test objectives, for example, on the spacecraft. I think that pretty well summarizes. I would not care at this time to go completely through the flight profile. I have some 60 pages of notes, and I think it would take a while. I think I'd just wait for some questions.
Before I mention the recovery activities, there were a couple of what I consider fairly significant steps taken and progress in the program here and the DoD support side. We did operate the Watertown, the Apollo ship, for the first time today, and it operated quite well and successfully. We also had 5 of the Apollo aircraft up today for the second time, and we got quite a bit of data, and as far as I can tell at this point, it is quite good data. They operated quite proficiently, were on their positions when needed and planned, and it was quite a good show. In the recovery side of the problem, we were responsible for recovering 6 camera cassettes, which General Phillips referred to, off of the S1, the S2 stages. We managed to locate 2 of them. One of them turned out to be damaged, I understand, by some reason, and we were just unable to get any sign, either electronic or visual, of the others. We presume that they just were not out there or sunk or something of this kind. I understand that the 2 we did get are quite important ones.
response, as Gerald Phelps mentioned, to the analysis problem. In the area of the recovery of the spacecraft, after the decision was made not to make the second SPS burn, the flight director and the mission director changed the aiming point some 200 miles west of its original point. At this point, we turned the carrier westward and managed to get it 100 miles closer to the aiming point, which put it just about 100 miles east of it. At the same time, we headed to Carpenter, which was approximately 15 or 16 miles west, eastward also, in other words, closing on the carrier, to get to the nearest point, which I understand we could expect a splash if we got a guidance and control system malfunction. We also reoriented the entire aircraft pattern around these two new locations of the ships. And since the aiming point now is some 100 miles west of the carrier, the task force in the Pacific decided to send two helicopters over 100 miles, somewhere between 100 and 140 miles west of the carrier to be at the aiming point at splash. Everybody was in position at splash time, and as it turned out, the spacecraft came down some 80 miles east of the carrier. We did get a number of bearings immediately before and after splash and before blackout. There was some variance in the bearings, but finally it settled down to where one of the C-130 rescue aircraft got a good bearing on it, let down, sighted the spacecraft, at which time the nearest helicopter with swimmers closed on the location some 35 minutes away, put swimmers in the water and collared the spacecraft. The spacecraft is now collared in the water with a helicopter cap. They will recover the swimmers, and the carrier should be there somewhere a little over 2 hours from now to make a night retrieval. That's about all I have to offer.
This is Houston, returning to the Cape.
George Alexander. Try going ahead.
Five. You were rather insistent that 503 would be unmanned, and now you seem to be leaving so many doors open that about 503 being possibly manned. Could you give us some explanation of your thinking on this point?
George, I never remember my being insistent about anything. But I'm not trying to leave any doors open. All I'm doing is trying to establish the set of facts that we have and the set of decisions that we will be making. As I told you at the time of 501, if we had another flight as successful as 501, if 502 were as successful as 501, we would seriously consider flying 503 manned. Now, 502 was not as successful as 501, and we still don't know, and we still have not been able to evaluate, though, what our problems are. And so we won't be in a position to make such a decision for several weeks.
I got it.
Go ahead.
William Hines, Chicago Daily News. George, I want to clear up one point and then ask you another question. You said on the negative side, we launched today almost 1 month from the day we planned to launch last year. Now, why is it, if you had a day selected last year to launch, that we were never able to get this out of you? I mean, we always have to wait until this quarter before you'll tell us when you're going to launch. Why don't you just level with us and let us know?
I always do, to the best of my knowledge.
Well, if you had a date set last year, which was 1 month, what was it? the 5th or 6th or 7th of March or something like that. We weren't able to get that out of you. That was classified.
Bill, as I recall, we announced the date of the March launch sometime several months ago.
I see. This is the date you're talking about. Okay, now the other question that I have is, how can you justify flying men on a rocket that's had one success and one, I guess you'd call it, partial success, when so much is riding in terms of money and prestige and everything else on this thing? Why can't you just go ahead and fly another unmanned Saturn and test this thing out and get the bugs out of it before you go and fly men on it?
Bill, that's probably the decision that will be reached. But in turn, we, as I said in the beginning of our discussion, our interest is in learning how to get to the moon safely. And we'll take those steps that will give us the most learning as we go forward.
Go ahead, Sanders. I believe you said it might be a matter of several weeks before final decision is made. It's our understanding that 503 would be ready to move to the pad before several weeks. What are you going to do? Are you going to tell them to go ahead and move, and if they have to bring it back, do so, or just tell them to hang on?
Well, you know, if we have to make any changes to 503 as a result of the of what we learned from 502, that will necessarily delay the moving to the pad.
But what if? They're pretty close to being ready right now.
That will depend on the results of the analysis. We won't move to the pad until we understand the problem.
Go ahead, Dick.
I'm a little puzzled, I think, by Dr. Miller's attitude on this. I have a note here which you're quoted as saying that on balance, a most successful mission. It strikes me that this is the kind of a successful operation in which the patient died. And I'm wondering if this is really the way you feel, or whether this is a euphemism, or do you really feel that this was a successful mission in terms of qualifying the launch vehicle for a manned performance?
Well, I think, as General Phillips pointed out, we were all disappointed that it didn't go perfectly. Yet it is from the problems that you encounter in one of these flights that you learn how to what the strengths and weaknesses of your vehicle are. I am particularly pleased that the problems we had, which could have been very major problems, in fact were accommodated by the system. The system is designed, as you know, to have margins of safety, to have redundancy that permits it to proceed even though you do have particular subsystem failures. And I think it is significant and heartening and rewarding that, in fact, the mission did proceed through the entire launch phase, even though we had a problem with the engines. And of course, we've designed it to be able to move forward in the face of problems. And in that sense, I would say that the launch phase, the launch to orbit phase, was quite successful. And I think we're all pleased with the results of that part of the mission, even though the engines did not burn to all of them to completion. I think that we just don't know what the impact of the failure to restart of the S-4B is at this time. I'd only point out that it is the most mature stage we have in our system at the present time. So it has more experience on it than any other stage, and thus far has been completely successful. It's the first time it's failed to operate completely successfully.
Corollary to that is also that do you feel that there is a relationship, or is there any indication of a relationship between these two engine failures?
Well, there's no present indication. We just don't know enough about them, though, to be able to say.
Go ahead, Mary.
Mary Bob Fairchild. I have two questions. For Dr. Miller, you said that if astronauts had been aboard, you could have gone on to a lunar mission if the S4B had ignited. It was my understanding that you couldn't have, because you used extra fuel on that longer burn due to the shutdown of the two of the S2 engines.
The best estimate that we had was that that we had enough extra performance margin to continue the flight on this one.
Let me, if I may, George, recap what I said this morning. And I think as we all know, this mission was not equipped, nor was it did it have all of the payload elements that are required for a manned lunar landing. It didn't have a LEM, for example, and the payload was less in its total weight, significantly, than a manned lunar landing payload. For that reason, we had performance margin in the launch vehicle, which would have wound up being unexpended propellant had the mission gone nominally. It turned out that the extra propellant used out of the S4B stage to achieve orbit did eat into that margin. We had enough propellant left to carry out the planned mission on this vehicle, but had we had to use up roughly 30 seconds of extra S4B performance to get to orbit on a manned lunar landing mission, that would not have left a performance margin to go on in a manned lunar landing mission to a full mission. And I think perhaps there's a small point of confusion. In this case, we were targeted for lunar distance in the second burn, and it did turn out that we had margin, in spite of the malfunction, to go ahead with that maneuver on this mission.
Thanks, Sam.
The other question I had was for you, General Phillips. Could you give us any details on the skirt separation of what was observed that was different?
I really don't have any further details now, and the photography and further data may indicate that it was normal. I felt that since in the meeting I had this afternoon, it was reported that it appeared different to the visual observers, that I should just make this fact known. Now, when the details are all studied, it may not have been different. And, you know, when you're talking about something, a visual sighting that far away on something that appears that small at that distance, it's pretty hard to judge what is different. It may not be significant, it may. We'll just have to see the data before we can say.
What instrument were you looking through, Sam?
This was long-range television coverage.
Go ahead, George. To follow, Sam, is the implication that the skirt may have struck the engine bells or something like that?
Well, the reason I bring it out is that possibility can't be ruled out until we see the data. Because the engines on into the flight certainly started malfunctioning in a way that we haven't been able to start to identify the cause of yet, and it's at least possible that there's a correlation.
Go ahead, Ed. Just a follow-up also. I'll get over to you.
General Houston indicated that one film cassette was possibly damaged. Do you know which one yet, and would it be the one that was taking the pictures you want to see? And if so, was the damage great enough to maybe hinder you?
What? We don't know here. Perhaps Houston does.
The report I have is that
General Houston in Houston, did you hear that question?
Yes, I did, and I don't know either. However, the impression I got as to the damage, that was mainly external and the kind of a thing that might have prevented it from floating, as opposed to the kind of a thing that might have had effect on the contents of the film. But I really don't know, and I can only presume that it probably is all right.
Okay, John.
John Wilford, New York Times. I'm a little bit puzzled on the S4B. Why is it that you never waited to exercise it again to see if it would reignite another time later? You rushed right into the separation, and that's...
Well, let me, if I may, pass that question to the flight director, who played a key part in planning the mission and the alternatives in the event of malfunctions, and let him answer that question.
Mr. Charlesworth in Houston?
Am I on? Well, actually, you can't delay it. It's all programmed to ignite on the second revolution in this case, and there's no way that we could delay and effectively try another ignition by any sort of ground command or anything. And the tanks blow down. Essentially, the IU sequences goes through its sequence, and your point of rushing into the separation, we did not rush. The IU attempted, it sent the signals, the engine did not light. We went into so-called time base 7 on the IU. It's programmed to start us into an attitude maneuver for separation. We waited until that time to be absolutely sure we didn't have ignition, that is actually starting the maneuver, and at that time we separated. So the answer to the question is there was no way to delay it for another rev.
We just had a news flash that is completely unrelated with the mission, but I thought some of you gentlemen might be interested. The news flash is that Martin Luther King apparently has been shot in Memphis, Tennessee, and is in very critical condition. Mark?
I'm not sure the question's important anymore. I didn't understand from Mr. Charlesworth why well, what I'm trying to say is we heard on the mission commentary after separation that there had been consideration of perhaps trying to restart the S-4B again during the several hours in which it still had battery life. Was there any consideration given to that?
Let me comment on, and then ask Mr. Charlesworth to comment. The fact is that the design of this system provides the capacity for one restart. In other words, we have the pressurization, the engine start bottles and the pressurants for one restart. And we spent those consumables to attempt the first restart, which failed. So those consumables didn't exist then to attempt another restart or to delay, as Mr. Charlesworth answered on your first question. Let me now ask Mr. Charlesworth to comment on the rest of your question.
Thank you. I wonder if you aren't confusing the reports concerning the question of whether or not to do the second SPS maneuver as opposed to trying to delay and do a reignition on S-4B. There were no plans to do that since we can't.
Let me say something here, please. All of this is in automatic mode, and after the computer on the S-4B sensed that there was not any buildup in velocity, it then automatically went into this time base 7 where it vented the engines, and you get rid of the pressurant and therefore cannot restart again. Sam, I'd like to also point out, however, that this is characteristic of this particular S-4B, that future S-4Bs do have a hydrogen burner which can regenerate the necessary pressure to go through a second restart sequence. And this is a very important part of a lunar flight because we may, in fact, come up on a start, decide not to. We could command that off from the ground or from the spacecraft and go around again and make a restart. So it is important in later vehicles that we have that feature.
Go ahead, Mark.
General Phillips, will that new S-4B be in the 503?
The feature that Mr. Kraft just outlined is in 503. It's a repressurization system.
So, in a certain sense, the 502 S-4B is quite different from the 503.
Not quite different. It is different in respect that the 503 and subsequent stages have a means of providing more than one pressurization cycle for restart attempts. It is, but that is a difference, but it is not a major difference in stages.
I just wanted to ask one more question, if I could. Dr. Miller, I believe you said earlier that the S-4B was the most experienced stage in the stack. But isn't it true that it has only been restarted once before, like the SC has only been flown once, S2 and so forth?
Actually, that was the only restart. We have, however, restarted the stage both in static firing and also in 203. We went through the sequence up to start.
Great, Bill.
I'd like to inquire of somebody, maybe in Houston, I don't know, why it was that there was such apparent confusion for a period of a couple of hours on the splashdown, well, maybe a period of an hour, on the splashdown location. We were all over the Central Pacific, it seemed to me. We went everywhere from right on the impact point to 375 miles off it, and this and that and the other thing, and finally ended up 60 miles away from the ship. What was all the confusion about? Why didn't we get some sort of a reasonable prediction of impact and stick to it?
Well, we did get readings which were at variance with each other, but I don't think this is anything that should be terribly alarming. We have a whole fleet of aircraft out there, and we are getting vectors, and they don't all just match up nicely the first time around. And these reports are conflicting until they settle down and you get a hard bearing and track it on in, and then you have a fix. And then we ended up with a visual fix, which is the real answer. So I will admit that we had various bearings that were in conflict with each other. They were probably, in some cases, as far out from the carrier as 75 miles, and in most cases within 50 miles of the carrier. But in the refinement of this, why, you can get confused, but you have to give it time to settle down, and finally it did, and we got to it, I think, in the process of about 45 minutes or an hour or something of that kind. We did have the forces deployed on the west side of the carrier. That's where the forces were. And the spacecraft did land on the east side of the carrier, and this may have helped a little bit to take a little bit of longer to settle the situation down. But that's the only explanation that I can give.
Okay, go ahead. Okay. Just to follow up on that, I don't suppose that anybody was really alarmed, but I think we were confused because of the really wonderful predictions we had in Project Gemini, where people were coming up with 6 or 10 miles, and maybe it would be refined down to 5 or 4. And I'm wondering if there is a different method of computation or some different set of parameters that you use in Project Apollo, and whether this is going to be a continuing sort of confusion, not a cause of alarm, but just a cause of confusion in manned flights, and particularly in manned flights coming back from the moon.
Go ahead, Bill.
You ready, Bill?
We were several thousand feet per second short of the velocity we had intended to reach. Therefore, we were attempting to fly what amounted to essentially a max lift or full lift trajectory, or as much lift as we could get. Under these conditions, you don't really know exactly what the lift-to-drag ratio is, and therefore you can't really predict exactly where you're going to get to if you don't have the capability of reaching the initial landing point which you'd intended to get to. Now, in the future, if we achieve the proper velocities at the time of reentry, you can be assured that we will be reaching the same kind of impact predictions and achieving the same kind of impact locations as we did in the Gemini program.